Okay, so today's lesson, as you can somewhat see here, is all about electricity and static and current electricity. They happen to be different from each other, and magnetism. Okay, and we've got some demos here. In particular, I had to steal this from some box I found in the J3 office, which is some big piece of styrofoam. And we've got some demos here that I will attempt to show you. As I mentioned right before to some of you guys earlier, the problem with doing some of these demos is that static electricity builds up much easier in very dry climates. And it happens to be like 90% humidity here in Djibouti, like all the time. So I tried some things earlier with the balloons before class, and they weren't as successful as I'd hoped, but we'll see. Hopefully we'll be able to do it. We may have to turn the AC off for a little bit, though. Yes?
Is it more susceptible to building up in a cold to dry?
Cold, well, if it's dry in general, that's okay. Colder and dry, yeah, sure. But if you've ever lived in like a cold climate where it's warm inside, but you can still like scrub your feet against the floor and get a big shock when you touch a doorknob or something, that happens. But yeah.
I thought of when I was reading this, why is it that when I go to open a car door in the winter, it shocks me, but everybody else getting in the car doesn't shock them?
Could be
because I was the first one, or is it because I built up more static electricity?
It's maybe because of your shoes, believe it or not. The way your feet, like your shoes, actually kind of insulate you. Hey, Mark, kind of insulate you from the ground. You get that. Now, we'll talk more about static electricity in a little bit. If you've ever seen, there's some countries actually. This is brilliant. They actually sell a little strip about that long that you hang off your bumper, and it just touches the ground.
So it grounds it.
And so yeah, so there's no buildup of like static while you're driving around, and then you don't get shocked when you get out. So it's kind of cool. But I saw that in Australia. I think they sold those. So go figure. Okay. Anyway, today we're going to do this. Alan, if you want to move one of these, we can move it if it's kind of distracting to you. Okay. All right. So let's start out. We'll try to do some demos here, and we'll go. Do I need to give a quiz on the chapters? No? All right. I'm not going to worry about it yet. There's a lot to cover tonight. OK. So this is one of my favorite topics because I happen to be an electrical engineer for my undergraduate degree. And so I know a little bit about electricity from that, although the stuff you learn in electrical engineering goes in a much different direction than some of the stuff we're talking about here, depending on what you study. I studied mainly computer engineering in the electrical engineering field. So some of this stuff was, when I started teaching physics, I kind of had to relearn it a little bit. But the bottom line is electric force is another fundamental force in the universe that we have to deal with every day, and we get to deal with every day. In fact, the nice thing about the electric force is it makes lots and lots and lots and lots and lots of things that we use every day actually so that we can create them. And actually, it makes it so that we can have chemistry, and we can have all this other stuff that's based on the fact that there is this electric force in nature. Okay, so it's fundamental. And the nice thing about electricity that's different about gravity is what? It's one thing about electricity that's different about gravity that makes it kind of important.
Attracts and repels.
There we go. Brian says it attracts and repels. That's a good thing. Gravity is of some use to us for certain things, okay? And it keeps us on the Earth and all that. But the fact that we can use electricity to actually attract things and push them away from each other makes it very interesting and very important for some of the things we want to create. Okay. That's electric force. It's a force. We'll get to what the actual formulas look like. Don't stress about the details about the actual equation, but it will actually seem somewhat familiar to you, I hope. The electric charge, okay? There are these particles, okay, and you guys have all heard about them before. They're protons and neutrons. Protons and electrons that actually have this fundamental quality to them that we call charge. Okay, it's fundamental. It underlies all electronic phenomena. Protons are positive. Electrons are negative. Okay, neutrons, what about neutrons? Neutral. They don't play any part in this whole electric game, except from the standpoint they provide mass. But as far as the electricity part, they do not play a part. In fact, that's one of the reasons it took much longer to figure out that neutrons existed, was because we couldn't use this cool electric force to like push them around and things. They just kind of didn't really appear until people started looking kind of in a more subtle manner. So neutrons took a lot longer to find because they have no charge. Okay? So yeah. All right. Aha, here we go. So the fundamental rule for electricity is, and you guys all know this, if two charges are the same, they repel. And if two charges are opposite, they actually attract. Okay? Now, I wanted to demonstrate this with the balloons here. So I tell you what, Tom, could you click off that air conditioner? Sorry, it might get a little warm in here. What I've got is I've got a piece of like legitimate fur from probably a rabbit or something like that. Okay? What's that? Exactly. Yeah, right. From somebody. Okay. And I've got a rod here that I can actually rub onto the fur, and it actually transfers electrons from one to the other. Now, I actually don't remember which is which, and I don't really care, but let's say that electrons end up going, well, first of all, it is the electrons that do the moving. Okay? In other words, the electrons are, we call them the negative ones. The only reason we call them the negative ones is because somebody made that up. It doesn't matter. We can call them whatever we want. Negative happens to be different than positive, so we call one of them negative. We happen to call the electrons negative, and they're the ones doing the moving. And if you remember what an atom looks like, remember how the protons and neutrons are in the middle and the electrons are kind of scattered around the side? Well, they're very movable, so they're the ones that are doing the moving. Which way they end up, I don't really care, but let's just say that the more electrons end up on this when I kind of beat them off the fur here. Why is that the case? I'm not really sure. I think the fur actually just, for whatever quality it has, it allows electrons to kind of like move onto other materials. And therefore, right now, after I've rubbed this around a while, this has a negative charge, we'll say. Okay, so there's actually more electrons on this than there are protons. Okay, so far so good? All right, now, if I do the same thing, the nice thing about rubber balloons is that they also, in a nice dry environment, tend to do the same sort of thing. So we'll say that when I'm rubbing this on here, I can do it on my hair too, right? And ooh, it's actually, I can feel it there. Okay, it's already working a little bit. If I rub the fur on here like this, okay, now this has lots of extra electrons on it, okay? And if I do it right, if things work out all right, I should be able to, there we go. Can you see how the rod is actually pushing away the balloon a little bit? I'm not actually, it's not because of the wind, it's actually because of the, oh, it actually attracted a little. So as I said, these, in this kind of environment, the static electricity kind of goes off pretty quickly because of the fact that it's so humid. Okay, so that's actually not working, although I can feel it. We'll get to what's going on right now, where it's actually attracting my hand. You can see that. It's attracting my hand. We'll talk about what's going on there in a minute. But let me do this. Let me try to do this. Hopefully, this in the past has worked pretty good. If I put a lot of negative electric charge on this balloon, and there's a lot of negative electric charge in the other balloon, what should they do to each other? They should repel each other. Okay, and they don't. Well, they kind of do. They kind of, there's a little too much weight on, I think there's a little too much weight, believe it or not. So they actually, you can kind of see that they go, they kind of, what happens is there's so much weight, basically, and there's not that much charge that they're getting close, they're bouncing off each other, and then they're repelling each other because the charge is spreading around both of them. Okay, so that's that. Now, the question is, there we go, now it's a little better. Can I do the opposite and get charges that actually attract? And where I've got now is a piece of like silk, and then there's this glass rod. And the glass rod in the silk supposedly does the exact opposite, where electrons end up on here, and this ends up more positive. So if I did it right, this would attract, and it barely does. Again, I don't think this works so well in this environment, but you can see I'm kind of getting it like that a little bit, okay? I mean, you can see it's doing it a little bit. A little bit there, it's going away. And if I did it right, I could probably make it like a swing, like you push right at the right time, and it could, still do that. But it's not working that well. There are, however, other ways to get charges in the opposite way, which we'll talk about in a couple minutes. Bottom line here so far is that we've got a fundamental rule: like charges repel each other, and unlike charges actually attract each other. So far, so good. And we kind of demonstrated that given the limits of Djibouti. OK, we already mentioned this. Protons are the positive ones. Electrons are the negative ones. Here's what the atom looks like, if you don't remember that from chemistry class. When we get to chemistry, we'll study this in a lot more detail. This circle here, they always talk about how, oh, the electrons are in these orbits like this. This is not quite proper. OK, there are no electrons. First of all, electrons do not orbit around like planets do around the sun or the moon does around the Earth. So just keep that in mind. The electrons can pretty much be anywhere in here. They tend to be about this distance away in that case. But we can take these off. And we can actually rip that electron off and transfer it to something else, some other thing. OK? All right. So atoms in general. By the way, let's count up here. This happens to be, anybody know what atom this is?
It
says in the book, what is it?
Helium.
It's a helium atom. Helium atoms have 2 protons. Remember on the periodic table, helium is 2. OK, on the periodic table? OK, has 2 protons, happens to have 2 neutrons in this configuration, and 2 electrons. So what's the net charge of this guy? Yeah, 2 positives plus 2 negatives gives you a net charge of 0. This is a normal atom, and atoms are generally neutral. OK? And this is actually a good thing. Why is this a good thing? Well, it's a good thing for a number of reasons. But it's a good thing because if atoms weren't electrically neutral, or if there was some substance which generally had lots and lots of extra charge in one direction, you would get things like lots and lots of static charge, number one. And number two, you'd get things like huge forces that you don't want to have to deal with. So the fact that most atoms are relatively are neutral is a good thing most of the time. OK? All right. So generally atoms have the same number of electrons outside the nucleus as they got protons. In metals, OK, they are what we call the outer the outer electrons are the ones we're going to kind of remove or add to the thing. They're nice and loosely bound. OK, electrons are generally loosely bound. They can move freely around the atom. OK, they can actually flow from one place to another, which is how I kind of got electrons onto the balloon. I rubbed the fur against, and electrons flowed onto the balloon. OK, and they can actually join up with other atoms. OK, which is kind of cool. OK, that's what's going on with the electrical atom. OK, we call these things ions when they have more or less charge than they normally do. OK, and we'll get into this in chemistry as well. An atom that loses one electron, OK, if it's got one less negative, it's going to be an overall positive, right? And so therefore, we call it a positive ion. If it gains one or more electrons, we call it a negative ion. It's fair enough? Okay. And notice that we didn't say gaining a proton here, because it's only the electrons that are doing the moving. Do you have a question, Kenny?
How would it lose an electron?
So if there's a situation where you're, say, knocking the fur against something, and the fur has all these atoms that have electrons that are really loose right on the edge, you can actually knock it away, and it'll go onto something it's more likely to stick to, like a balloon. It's definitely more subtle than that, but that's kind of the idea. OK?
So when an electron is lost, does it become a new element?
No, electrons do not form by themselves into elements. They're always with some atom or another, generally. Now, you can have an electron beam, like one that's in your old-style television. OK, you can have an electron beam, and what happens is that the electrons travel through space for a while, and then they hit like a screen, and then you see a little bit of light from it, and then they kind of get recycled back into the system, if you will. So they can be by themselves, electrons. You generally don't see them by themselves, but they don't form their own new atoms. Atoms have to have protons in order to be an atom. OK, and in fact, if you have like an atom with no electrons, it's just basically a nucleus. And you still kind of can call it an atom, but it's a nucleus of an atom. OK? All right. So the amount of work that you get from pulling these electrons off of atoms varies. Some things are very good at it. Something like this styrofoam happens to be very good at getting electrons onto it. Okay, so you stick the balloons, generally pretty good as well. Okay, and metals are also very good at moving electrons around. Okay, this is one of the reasons that they're very good at conductors of electricity and heat, by the way, because they have these free electrons, which are very easy to move around the substance. Okay, and you actually have more work to actually pull the electrons off of things like rubber. So they generally stick to the rubber better and or kind of go onto the rubber better. And other good insulators, it's harder to move them around. Okay? And when I say insulator in this case, I mean electrical insulator. Okay? Things that do not conduct electricity very well. Okay? All right. So here we go. Conductors and insulators. Electric conductors are what you think. They're things that allow easy flow of charged particles, generally metals, good conductors. Okay? You happen to be a conductor, but mainly because of the salt water in your body, right? That's what makes you a better conductor. Okay? It's the outermost electrons we really care about. The innermost electrons are actually so close to the nucleus, they actually get pulled in by the protons and stay there. So don't worry too much about that. Electric insulators have these tightly bound electrons. Okay? And metal, good insulator, rubber, metal, good conductor, rubber, fairly good insulator. Might as well say it right now. What makes it so that maybe we'll get into this later, but we'll talk about it now. You know how they always say, if you're in a thunderstorm, go sit in your car and you'll be fine? Why is that? Because the tires are rubber, because your car's a conductor? What do you?
It's a good conductor. It may attract thunderstorms.
Might attract thunderstorms? No. Well, no, not quite. Okay, it's the rubber. You guys all, it's the rubber tires, right? Yeah, no, it's not. It's actually, Louis is actually correct in that the car itself has a lot to do with it, right? Okay, it has nothing to do with the tires, believe it or not. Those tires, if you think a bolt of lightning is going to travel a mile to get to your car, it's 25 million volts, it's going to get to your car, and then it's going to be stopped by like a 1/4 inch of rubber? No, it's going to go through all that air, which is a terrible conductor. Right? Not the tires. Okay? Happens to be because the shell of the car is a good conductor. The shell of the car is generally metal. Okay? It's probably not the best to sit in one of those fiberglass Corvettes or something like that in the middle of this, because it's But from the standpoint that the car is metal, what happens is the electricity travels around the edge of the car and then into the ground through the tires. Actually, in fact, sometimes you can blow your tires out from getting struck by lightning. Okay? But it doesn't have anything to do with the actual tires themselves, because that's it. Now, by the way, rubber is a very good insulator, but it's not a perfect insulator. The wires that, ever seen those high tension wires, the ones that are on those big poles, and they go from like across giant fields and from various places, those things sometimes are up to like 125,000 volts. They don't even bother covering the wires in rubber. They don't even bother. Because what's the point? If you really could get up there where there was a situation where you were going to get electrocuted, that little film of rubber is not going to do any good with that much voltage. They don't even bother, right? So they're just bare wires.
So they keep them like live wires?
They're live wires, sure. But they're just bare because the reason it doesn't really matter with that much voltage about the rubber. Okay? Things like 9-volt batteries, sure, you can use rubber to like insulate yourself from that, or the wires we're going to use in a little bit. Okay? But anyway, that's that. Okay, so here's a quick check question. You brush Fido's fur and you scrape electrons off of it. The charge of Fido's fur is now going to be what? Positive, negative, both, or neither?
Negative.
You scrape the electrons off of it. Positive, yeah. Now, really it's A and B because it's going to be some positives and some negatives, but less negatives, so that's it. But we're going to go with positive in the sense that overall the net charge is going to be positive. Okay, and then you go and you touch his nose and he barks and whatever. Okay, so the electrons are scraped off the brush onto Fido's fur, would be the other way around. Okay, all right. Here we go. Just like with energy, we're not creating any charge. The amount of charge in the universe is fixed right now. Okay, it's completely fixed and it's a conserved property. In other words, you're not creating them when you're rubbing these things against the balloon, the hair against the balloon. You're just transferring them. Okay, fair enough? Transferring from one to the other. Okay, so far so good? All right. Let's talk about this actual force. Okay. For a pair of charged objects, in other words, let's say that I had these two cans were charged. We're going to use these cans for something else in a little bit, hopefully. These two cans are both charged, right? For a pair of charged objects, much smaller than the distance between them. Much smaller than the distance between them? The force, I don't know what that means actually. Why did I type that? For a pair of charged objects much smaller, oh, sorry. What that means is we can't really talk about big objects when we're talking about this because there's charge that can kind of flow to one side or the other. But we're talking about little like point charges and things. The force between them varies directly as the product of their charges and inversely as the square of the separation of the distance. Does this look familiar?
Yes.
Two masses divided by distance squared. What was that formula? Gravitational formula. Very good, Nicholas, right? That was the gravitational formula. And this formula looks exactly the same, except instead of big G for the constant G, we use this constant K, which is the electrostatic constant. What's that?
Not kilowatts.
Not kilowatts, no. We'll get to what watts is in a little bit. But the K stands for the electrostatic, I think it's the electrostatic constant. And I think that's what it is. We'll find out probably on the next page. And it is actually just the constant that makes this formula work for the amount of force. OK. When we talked about gravity, was gravity a strong force or a weak force? It's a very weak force because remember, it takes the entire Earth to hold you on the ground, and then you can jump off it with just your tiny little muscles, right? Even if you skip leg day at the gym, right? OK? You can still jump off the Earth really easy, and that's the entire Earth holding you down. OK, so gravity, although it feels to us like a strong force, and if you fell off a building, it certainly would smack you against the Earth pretty hard. It is actually a very weak force. Now, electricity, on the other hand, electricity, on the other hand, has a proportionality constant that's this big. So by the way, if we're measuring charge, like in other words, so many electrons have such an amount of charge, we call that charge so many coulombs. It's just a unit. We might mention coulombs in a little bit. But the charge on an electron is this tiny little amount of coulombs. 1.6 times 10 to the negative 19th. Let's see. 10 to the negative 9th is a billion. So 18th is a billion billion. So this is 10 billion billionth of a coulomb. Not a very big amount. Now, the interesting thing is that there's lots and lots of electrons in things. OK, so yes, each electron is a very, very small amount of charge, but there's lots of them. This proportionality constant is 9 times 10 to the 9th, and then this weird straight string of units, Newton meter squared per coulomb squared. Don't worry about that. But it's a relatively big number. This is this is actually 90 billion is the amount of that number. OK? All right, remember, if you've got like signs, you're going to have a repulsion charge. OK, so you're going to go apart. If you've got unlike signs of charge, either negative or positive, you're going to have an attraction. OK, so that's the proportionality constant and the fact that it's attraction. Now, if you'll recall, the gravitational constant, which is similar to the K here, 10 to the negative 11th versus 10 to the 9th. OK? That means that G is 100 billion times smaller than this number here. So there's where you get the idea that gravity is a very, very small force. The proportionality constant is tiny. The proportionality constant for electricity is huge. OK, so that's why when we do rub fur against the balloons, those tiny little balloons can actually separate from each other just by having different charge on, an amount of charge on them. Just a little bit of charge can separate those because the electric force is much, much, much bigger than the gravitational force. And in fact, when I did this, I'm gonna try it again here. When I did this, if you let's do this again. If you do this up here like this, okay, and then I have the other one here. If I do this right, I can actually move this against gravity, right? I mean, I've seen it before where I can actually make the balloon go up in the air just from a tiny little amount of electrons on here. This one not working so well here in the classroom, but all right, well, we'll see what we can do here in a minute. OK, any questions on like the difference between gravity and electricity in terms of the size of the force? Okay, on a test, if I say which is the force that's really stronger, gravity or electricity, you're going to say electricity, right? OK. All right. So here's the differences between Coulomb's law, which is electricity, the force of electricity, and Newton's law of gravitation. We already said this. Gravity just pulls together. It all does. OK. And by the way, we understand. You'd think it would be the other way around, but we understand gravity way less than we understand electricity. Part of it's because it's such a small force. It's tough to like do real experiments on it. But gravity only attracts, electricity attracts and repels. Both forces can act between things that are not in contact with each other. OK, notice when I put the rod near the balloon, they didn't touch each other, but they were getting pushed away. OK, and I think I mentioned this at the beginning of the year, but when you're standing on the ground, do you know what keeps your feet from going through the floor?
Gravity pushing up, the force of the ground pushing up on you.
The force of the ground pushing up on you. Yes, but where does that force come from? That's really the question. I wonder if you can see this. It's not friction. Friction is caused by like the atoms being close to each other, but
Strength of the atom
Tyler's saying it's the strength of the atoms. What strength?
within the floor that's holding it together.
Okay, but what force is that? A gravitational force or an electric force? What do you think? It's an electric force. Here, let me draw it like this. Here's the ground, and here's your foot. Okay, forget about my bad drawing skills. Okay, here's your foot, here's the ground. In the ground, there's a bunch of atoms. Okay, they all have negatives along the outside of them and positives on the inside. Okay, your feet have the same thing. A lot of negatives around the outside and positives on the inside, and there's billions of these things in your feet and in the ground. Negative, 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 and positives there. When these atoms get really close to the atoms in your feet, what do those electrons, which are the same charge, do to each other? They push against each other, right? And what happens is because the atoms aren't moving because you're wearing solid shoes and the floor is solid, okay? The electrons here get kind of close to the electrons here, but they push them up and they do that. So you actually never touch the floor. As it turns out, you're always hovering a little bit above the floor. Nothing's really ever touching anything, except in some sort of weird quantum mechanical sense. There's nothing actually touching. The atoms in your shoe get really close to the atoms in the floor, and they kind of hover there. And there's so many of them that there's that little layer right there, and you can't go between them. So, by the way, you look at all these science fiction movies and you're like, oh, there's a force field. Well, we've got force fields. Like the floor is a good force field. This wall is a good force field. Okay? From the standpoint of what's keeping my fist from going through the wall, well, it's the atoms in here, which are really just a force field. Kinda. I mean, if you want to think about that. And then everybody said, well, what about a clear force field? Well, what could I make this wall out of? Glass, sure, plexiglass or something like that. They can make bulletproof plexiglass, right? It's just a force field. I mean, it's in some sense. You have to be a little creative in thinking that. But both gravity and electricity forces act in a straight line between the two objects you're talking about. Okay? And there's this force field around both, which is based on how much mass or how much charge, whatever it is you're talking about, has. Okay? So there's there's many similarities between gravity and electricity. Okay? There's also some differences, like they attract and repel for electricity. Okay? All right. Another check question. According to Coulomb's law, okay, a pair of particles that are placed twice as far apart, same question as the gravitational force one. If I have a particle here and a part here, if I have these two particles, okay, and they're here, they're going to have some force between them. And then I make them twice as far apart. what's the force going to be?
Quarter is strong.
Well, first of all, is it going to be bigger or smaller? It's going to be smaller because they're farther apart. So that takes out twice and 4 times. What kind of force is this? An inverse square law? Twice as far away means, no, that would be a quarter as strong because it's squared. You take the 2, twice as far, square it, and then say, oh, it's on the bottom of that equation. So you say, oh, it's 1/4 as much. OK, so it's got to be a quarter. OK, you can do that. Here, on the test, I might ask you another one like, OK, I take 2 particles, and I then move them 5 times apart. How much force is there now?
5 times less.
Not a 5th. Did you square anything? No.
Well, 25 times less.
25 times less because you square it. 5 squared is 25. Get that in your brains.
What happened to the inverse?
The inverse, 25 times less force because you're farther away. Right? I know it's a little. It takes a while to get this through your brain, but that's what it is. Okay. All right. Now, when you have 2 atoms near each other, okay, and nothing's getting ripped off, okay, molecules in solids, okay, molecules can't actually move away from their positions in solids. The molecules themselves don't flow through these solids. The electrons can actually do some flowing, okay? And in fact, the centers of the charge can flow. But basically what's going on is the proton stays where it is. And the electron cloud kind of shifts a little bit, one way or the other, depending on this force from whatever else is around there. Okay, so notice in this one, the positive charge is over a bit. The center of the negatives is here. So they're separate from each other. Okay? All right, so you've got this charge, this atom here. Now the charges are a little bit separated from each other. Well, what that means is, instead of being neutral now, it's actually what we call polarized, which means it's got 2 sides which are slightly different charges. Okay? This is kind of cool. Now, I forget if I have another. This is why, and I don't think this is going to work here, but this is why you can actually, in a nice dry room, you can take a balloon, rub it on your hair, and then stick it to the wall. You ever tried that and it works? Okay. I don't think these ones will stick to the wall. I guess I could try it. In fact, I'll try it with one of them. But I don't think it's going to work only because it's so humid in here, and these walls are, I don't know what they're made of. But here's what I'll do. I'll try to do this. Let's see. If we take this, okay, you can do this. You can make this slightly charged here, and then it would if, well, you notice that it stayed right on the wall. It didn't kind of come off. I don't know if you can see it. It wouldn't like bounce off very well. That time it did. Well, anyway, the point is that what's going on is this. Let's look at it this way. The balloon has a bunch of, you can kind of see these little blue things on the balloon. Those are the negative charges. The balloon has the little electrons on there. The wall, this separation of charge like this happens a little bit in the wall. Okay, because what happens? The electrons in the wall say, I don't want to be near all these electrons on the balloon. So they start heading this way a little bit. Okay, well, that leaves the positives here. Well, what do positives do to negatives when they're close by? Attract. They attract. So then the negatives in the balloon attract to the positives here. They don't attract as much to the negative, or they don't repel as much to the negatives over here because these guys are farther away. Okay, Lou, are you going to make it? You're not making it here. You can stand up if you need to. So the negatives in the balloon push away from the negatives here. They push them into the wall a little bit. And then the positives here can have a bigger force of attraction to the balloon itself, to the negatives in the balloon, and therefore they stay together. Okay? So we can actually demonstrate this a little bit. So let's see. I'm going to try to do this here. This, what I've got is just a piece of styrofoam, which I said is a pretty good, has a pretty good ability to give up or I guess gather electrons here. Okay? And you can actually feel it. In fact, I should have everybody come over here. In fact, why don't we do that? Everybody come on over here, because I want to show you this. Everybody gets a chance to check it. Hey, Bobby, before you go, why don't you aim the camera right here? And then what we'll do is we'll move the...
So is there a time that rapid first is going to
No, actually, that was a good question. The rabbit fur is not going to lose all of its potential to give up electrons, because what it's doing is it's kind of getting some out of the air as well. It's kind of they're kind of it's off now, but then over time they leak back onto it. Okay, so come over here. I'm going to just rub this against here. Everybody come over here. Put your back of your hand down there. Can you feel that? You can feel like okay. Tell you what. Let's wait on, because I'm going to use that. I'm going to use that in a minute. So it'll be all right if it's in the middle, or okay. Go ahead. Put your hand back, the back of your hand there. Can you feel it? Yeah. Okay. Try it, Kenny. Kind of. Can you feel that right there? Okay. So this definitely means there's a little bit of a static charge on there. Everybody try to do that. Even though, can you feel it? Yeah. Okay. Feel it over there? No? Let's try it now. No? Maybe you have really humid skin or something. Did you feel it? Maybe you don't have much hair on your arm. Try back up. Try like the upper of your arm there. Can you feel that? Yeah. Okay. A little bit. Okay. Try it. Go ahead. Can you feel that?
No, really.
Put your hand right down there, kind of slowly. Do you feel that like push back up on you there? That's the electric charge right there. That's good. Go ahead. Not bad. Give it a shot. Let's try it. You feel that? Okay. Who else hasn't tried it? Go ahead, Ann. Can you feel it all? Yeah, it's pretty cool, huh? Go ahead, Bob. Give it a shot. Okay, so feel that? Well, hold on. I haven't. You guys, you're not free quite yet. Okay, come on over, Tom. You can feel it.
No, I already did.
Oh, you already did. Okay. So now, here's what's going on. We've got lots and lots of charge built up on this styrofoam. Okay, lots of charge built up on styrofoam. I have a metal little pie plate thing or plate thing that I've stuck on here with I've stuck a little plastic piece that's a very good conductor on here. Okay. Now, if I take the metal and I put it on here like that, there's electrons, lots of extra electrons on the styrofoam. Okay. Where have the electrons in the pie plate gone in terms of the bottom of the plate? They've moved up, right? Because they're going away, because they're getting pushed away by the ones here. If I take my grubby little finger and I touch, I actually got a little bit of a shock. Whoa, okay, I'm going to let all you guys try that. And then, now, I've actually grabbed more electrons and pulled them onto this guy here. Okay, and if I do this on my nose, I got a little shock again. I don't know if you heard that. But you can do it, right? And sometimes you need to do it on your thing. But I want everybody to try that again so you can see this. So what's going on again is, in fact, I can probably do it again. Yeah, like that, and then just click again like this. So come on over, try this again. I want you to kind of feel what's going on here. Okay?
So the styrofoam takes electrons from the rabbit skin, and then
Styrofoam takes the electrons from the rabbit skin. Okay? Yeah.
The tin wants to repel it, and then you pick it up, and then when you pick up the tin, you give it its electrons back.
Yeah. So here's what's going on. So basically, the electrons there are now mostly on the top of the aluminum here, right? And then I go down and I say, I'm going to give those electrons a path to leave that, right? So I touch it, I get a little shock, and then the electrons have gone, woohoo, I can go away into my body, which is kind of large compared to the rest of the stuff here. So that leaves less electrons there to actually be pushed away. So when I pick this up, it's actually going to be positive. But I can see that now. Now I go and I touch it again, and I get a little shock again. And that means that the electrons go back out of my skin into this. So now this is neutral again, and I can't touch it again and get another shock. OK, so try this. Come on over here. Come on over here. OK, just touch right in there. Did you get a little shock? OK, and if you pick it up and try it again, did you get another little shock? Yeah. OK, so try it. Next. I don't even have to redo it at this point. Go ahead. Yeah? There you go. It's kind of cool. Go ahead. There you go.
From the styrofoam or repelling.
When you hold my heart monitor, it doesn't give out on me.
You have a heart monitor? I know. So there you go. And then there you go. OK, it actually kind of, you can definitely feel it. So you made it? You made it? All right. Did you touch the side?
Yeah, you touched it.
That probably won't work, because you're not getting enough electrons for your whole body to really make it work that well. Okay, but
So will it still transfer to this?
I don't know. Let's see. Yep. But that's because this is now very positive, and you actually are going to be. You're a pretty big reservoir of charge, even though you don't really feel like you are. You're a pretty big reservoir, so that's how you can do it. Go ahead. There you go. Did you get a nice shock? Same thing, shock? All right. Oops, I did touch it that time myself. OK, go ahead.
So just touch it anywhere?
Right in the bottom there. There you go. And then touch it again. You get another shock, right? But if you touch it again now, nothing, right? Because you already gave back all the electrons that you took off the first time. OK? Go ahead. Oh, you got it from the side probably. Did it work, or did it the second time? OK, try it. When do you guys try it?
So, if it, put it in the...
Did you get a shock? Not sure. OK, hold on. Try now. How about that time? You did? Did you get it? Yeah.
You can hear it.
Right, you can actually hear it. Yeah. And even in the humid weather. Go ahead, Tom.
No, you asked me.
There you go. Nice. What happened?
No, you said like going like this, sticking in the.
Oh, and that, yeah, don't do that. There you go. Good. That's pretty cool, huh?
It
All
almost
right.
knocked me down all over.
All that electricity knocked you down.
Hard.
Well,
Hard.
believe it or not,
Good thing I don't have
we'll talk about. Did you get a shock the second time?
Yeah.
Did you? Try it again. I didn't hear it.
Wonder what would happen if I had a picture.
Yeah, I heard that one.
Oh, with this.
There you go. I did hear that one. All right. Anybody? Oh, go ahead. There you go.
You don't want to stick your.
There you go. Okay. And this will keep working for. Whoops. This will keep working. Ow.
No.
Be what?
No, he said, I wonder what would happen if you had a pacemaker. I said, probably nothing with that. I said, but you don't want to stick your tongue in that.
No, you don't want to see your tongue in that. Well, believe it or not, this probably has close to 5,000 volts when you do that. Right? There's probably close to 5,000 volts right there. Now, we'll get into the details of why this isn't going to kill you. And it's kind of the same. It's the same idea as the sparkler the other day. Remember the sparkler where
Low charge?
it seems it's a number of charges, but overall the total energy is just so small. Yeah, voltage. We'll get into what voltage actually means soon, but total charge is very small. Now, let's see if I'm going to try one more demo with the balloon itself with this idea here. Let's see if we can get this to
How
work.
many volts does it take to revive somebody?
Well, that's actually a good question. How many volts does it take to revive somebody? Depends on, you got to get it perfectly correct through the person's heart, right? And it's not really about the voltage. It's about giving it enough like startup current, which is actually very little, which we'll talk about in a bit to get it to do that. OK, so there's my balloon. This is actually going to attract to my hand. Oh, it's working better now, right? Attract to my hand pretty well just because my hand happens to be polarized, right? Let's see if we can do this. If I do this, and then put this on here and touch it, what did we say this should be now? Should be positive, which would do what to the negative balloon? Should very much attract it, right?
Nice.
OK, and you can see that a lot, OK, because that's very much attracting it there because of the thing. Now, if let's see, is there a way to get? Oh, aha! This is the other one I wanted to show you. OK, I need two people to help me out with this one. All right, let's try this. And not quite levitation, although I just did levitate that balloon, right? A little bit. OK, we need one other person here because I can't do both things at once. You hold this one, Tom, and then come on over here and hold this. OK, here's what we're going to do. I'm going to try to actually make one can one charge and the other can the other charge by this cool idea called induction. Charge by induction. Here's what I'm going to do. I'm going to use this guy because it seems to be the best carrier of electrons right now. Here's what we're going to do. You guys are going to touch those two aluminum cans together at the ends. OK, just like that. Yep. OK, no, just hold them together. Hold them together like that. OK, here's what I'm going to do. I'm going to make this very much charged up. So what am I, and lots of electrons on there. Where are they pushing the electrons in this guy? To the green one, right? Now, if you pull the green one away, OK, now the more electrons should be on that one, and this one should be positive. See what happens. It might not have quite worked, but see what happens when you push that toward it. Should repel it. Okay, whoops. I think your hand might be. It might be there's too much polarization here going. Let's try it. Here's what we'll do. We'll try it again with this. Try it again with this one. So it's got lots of charge. So put them together. OK. And then if I get this really close and then touch one side, OK, pull them apart. Oh, I didn't need to touch them. Sorry. Do that again. Sorry. OK. If I put it really, really close and then get that in there like that. Now pull yours apart. OK. And then now it should be pushing that away. It's not working. Try yours. Try yours again. Right there. Just see what happens. No. No, it's yours is actually, yours might be charged a little bit more, but I'm not sure. It might be your hand too. Okay, so I don't think this is really working well, but let me draw it up on the board what's supposed to happen. I think we're done with the balloon right now. Okay, anybody want a balloon? All right. Okay, you want to just aim that back over here, Bobby? So can you get the whole board here? Awesome, okay. Okay, so here's what should have happened. Okay, let me do this. Let me block this out for now. Here's what should have happened in that demo, but I didn't do it very well, I guess. This was the can, one can and the other can, like this. Okay, and they were on sticks that were hopefully insulators. I brought the negatively charged styrofoam near it. Okay? In here, there's some negatives, and then there's some positives. Let's make the same amount. 1, 2, 3, 4, 1, 2, 3, 4. 1, 2, 3, 4, 1, 2, 3, 4.
You got 5.
Thank you. All right. Oh, how's that? Boom. One, then 1, 2, 3. There we go. Now 1, 2, 3, 4, 1, 2, 3, 4. Okay. Before I bring the styrofoam over, it's nice and everything's spread out evenly. We're good to go, right? I bring the negative one over here, okay, on the ground. Thank you. I bring the negative thing over here. What do the electrons in here want to do? They want to go this way. So I'm going to actually erase a few of them, okay? I'm going to leave one because it's probably still have some. But 1, 2, 3 extras, okay? This is now positively charged, and this one is now negatively charged. And if I actually separate this one away and pull it away a bit, right? Let's say I do this. I pull it away a bit, like that, right? Then now this one should be positively charged, and it should have attracted the balloon, which we also said was negatively charged, but it didn't seem to. And the other one would do the exact opposite. It's got, well, this one should have attracted it. This one should have repelled it away. Okay? But it didn't seem to work very well, and I don't know if that's because the aluminum cans didn't work very well or what, but that's what should have happened in that. And that's called charge by induction, which is kind of a cool idea there. Okay? All right. Any questions on that? Okay.
You could go from the styrofoam to the tin bowl to the can to the balloon?
That might work. The styrofoam styrofoam to the tin, to the pie plate one, and then to the aluminum. Maybe you might have been able to, yeah. But from the standpoint of, yeah, you might have been able to. I'm not 100% sure though. We could try it, but you guys will have to come back in like August when it's really hot and not so humid or something.
So could you have done the styrofoam with the rabbit pellet and then had a hand on the tin foil, set it on the styrofoam, let go, then pick up the styrofoam again and tap it and tap it? Is that how it's working?
Well, let's try it. I think this is what you described. You said do the fur on here, yeah. but have this already on here?
No, hold that with your hand.
Whoops.
So if you
okay.
Styrofoam.
Okay, against what?
Against
here, yep. Okay.
And then I take this that I'm
I
already
see.
touching. Do I have the charge now? And I
don't know. Yeah, there you go. That was actually good. So you actually, whoops. So you were holding it, and when you put it down, the charge has lots of place to go through your body, and then you let go. That's what you did. Yeah, you let go, and then now this should have lots of charge, and then, yep, you get it there. You can actually hear it. There you go, Bill Nye. There you go. All right, good, very good. All right. Okay, so that worked better than I had expected after my test this morning. Whoops. I kind of mentioned this about the amount of voltage on here. Okay. We call voltage, by the way, electric potential. We also have potential energy, which I actually skipped from it's in the book, but I'm not really going to make you worry about electric potential energy. What I want you to think about is this thing called electric potential. We normally just call it voltage. Okay, you've all heard of voltage before. Okay, you've all had used batteries before, like these guys, okay? On the side of your battery, it says how many volts something is. Anybody know what a AA battery voltage is? 1.5 volts. Yep, it says right on there, 1.5 volts. Okay? So what does that actually mean? That actually means when you say the battery has 1.5 volts, it means the amount of energy per charge. Now, there happen to be a lot of charges in here, okay, and a lot of stored up actually chemical, as it turns out, chemical and metallic kind of together, chemical energy in here. Okay, that chemical energy happens to produce a voltage, meaning the amount of energy per charge across here, which is 1.5 volts. Anybody know what the difference between a 1.5 volt Duracell, or sorry, a AA battery is, and a 1.5 volt D battery? They're both still 1.5 volts. So what's the difference between the D and the AA?
The size?
The charger on top.
How about the what?
Are both chargers on top compared to that? That's
No, no, a D. Hang on. I got a D battery in the other room. Hold on. Hold on. Hold on. Just so everybody knows what we're talking about here. Let me grab it. We've seen the D batteries before when we did the mass thing. All right. Can I see those scissors right back there? The blue ones? Thank you. Thank you. All right, so, hang on. Whoops. There we go. All right, so this, there we go. So this, I feel like I'm doing an ad for Duracell. This, I'm going to put that on the YouTube video. I'll put Duracell, and then hopefully it'll give me some money. Sponsored by Duracell. That's a D battery, and that's a AA battery. And if I look on the side of the D battery, it says, doesn't.
It doesn't.
That's odd, but it's 1.5 volts as well. Oh, it does. There it is. There it is. It says 1.5 volts. Okay, and this is 1.5 volts. But why would we ever want to use these with the same voltage?
Well, that one carries more charge.
Ah. And Nicholas says it has more energy. The amount of energy per charge is the same. Well, it's not about how much is coming out. It's about how much is there to come out. If you could take this and connect it up to your, I don't even know what people use anymore that have AA batteries, but I was going to say your phone, but phones don't use AA batteries anymore. I don't know, cameras, a remote control or something. You would get much longer use out of these than you would these because there's just more charges, and so the total amount of energy is much bigger. The amount of energy per charge, same, as it turns out. Okay? All right. Whoops. That's all right. Okay. So when we look at the number of volts, okay, we actually say 1 joule per coulomb. Now, I said on the balloon and on the styrofoam and on the little pan thing here, it can be up to like 5,000 volts, just right there. Well, that doesn't actually kill you because when I do this, and by the way, you're not going to sit there and run your whatever your CD player or whatever you do off of batteries, right? You're not going to do that by like the tiny little amount of charge I put here. You can feel it because your body's pretty good at feeling those kind of charges, especially when it is 50,000 volts. But it's much like the sparkler, where the amount of charges on there are there's not that many charges, but the energy per charge is very big. Well, you can actually get a spark like when you felt it there. Okay, high voltage because the energy per charge is very high, but the number of charges is not really that high. Now, it might have been, by the way, it might have been billions, but it's not, trillions or whatever. Okay, so that's what there. And that's why we might have a nice harmless balloon, even though there's lots and lots of voltage, a nice high voltage. Okay, all right. Here's a question. This one's a little off of what we already talked about, but it's something we should be able to figure out. When you buy a water pipe in a hardware store, you don't get any water, right? You got to supply your own water. When you buy copper wires, do you have to give the copper wire the electrons, or are they already there? They're already there. Now, it's the electrons, much like the water, which is going to actually do the work that we're going to talk about when we get electric charge flowing. Okay, so they are already in the wire. Can they fall out of the wires? No. I don't think they can fall out. Okay, it's already there. Okay, tell you what. Oh, by the way, when you get an electric shock, the source of the electrons are either in your body already, like when you got the shock when it was up like this, right? Or they're coming from whatever the substance is that you're touching when you do that. Okay, you get the that's where the electrons come from. It's not that the electrons themselves. Well, when you touch here and you get that little shock, there's a tiny little number of electrons that does go into your finger, and then kind of it's a chain reaction. The rest of your body kind of gets that feeling from it. Question?
Do we? I mean, what are we considered? Negatively charged?
What are we considered right now?
Yeah.
Do you go around shocking things right now? If you touch the guy next to you, if you touched Eric on his head, would he shock him?
Sometimes it happens.
Sometimes it happens because you maybe been scruffing your feet on the floor or something like that. So then you might get a little bit of buildup of charge. But right now you're basically neutral. Most of the time we are. Okay, most of the time we are. Okay. All right. Tell you what. Let's take 10 minutes now, and we will come back and continue on. Okay, thanks, Tom. All right, so let's get back to voltage sources. Okay, remember our battery, D or AA, is a voltage source. Okay, it actually provides a potential difference between one side and the other. One of the sides, by the way, we call positive. The other side we call negative. Okay. And batteries, generators, the alternator in your car is a good voltage source. Okay? And what we say is, this is kind of an analogy. Well, this is actually true, but charges will flow from a higher potential to a lower potential. Okay? And what that means is if the voltage in something that we're going to get into circuits in a little bit. When the voltage goes from, the charge actually goes from the higher voltage to the lower voltage. And basically, you can think about it a little bit like this. Inside here, you can think about all this energy in there. It's basically when you connect a wire from one side to the other, the charges have a lot of energy. They want to get away. Let's say the negative charges want to get away from the positive charges. They go flying out one end, kind of to the other end. It's kind of the way, not quite perfect, but it's kind of the way it's going. Yeah, Tom?
That's how a heating coil in an oven works, right?
A heating coil in an oven. Well, heating coil in an oven, an electric oven, is a circuit. Yes, and we'll get to circuits in a little bit. What's that?
That involves resistance.
It involves resistance, which we'll get to. Okay. All right. So charges flow from higher potential to lower potential. Okay. And then they stop when you end up getting the same potential, and that's basically when your battery dies. If you're talking about a battery. Okay. This is the analogy here. It's like if you had water and you somehow got it into this situation where there was a higher one up here. Remember, this isn't going to happen in real life. What would happen is the water actually goes down to the lower potential, the lower pressure in the water. What we can do, though, to keep the water in this form is we can keep pumping water up to up here, right? And it goes down here, leaks out, goes this way. The pump is what needs to be there so that the water doesn't just kind of level out and stop flowing. In order to keep the flow, you need some sort of pump. Well, guess what? In electricity, the battery is what the pump is. It's a charge pump. You could think about it that way. It's the way it pumps charges around this situation from this actually pumps the charges through the circuit that we're talking about. Okay. All right.
So what's the cross section that it says there?
Which cross section?
It says cross section in front of the pump on the substance side. Does it mean like an orifice?
Yeah, this is like just the size of this in here. I don't know why it has the cross section, but it's saying that it's taking the water here at the lower pressure and pumping it up to the higher pressure area.
Okay.
That's what it's doing. Okay. All right. So again, if you look at a water pump, okay, let's say you had like a line on here this is kind of a weird analogy. I don't really love this. But if you've got the water pump here, you can have a valve, and a valve just turns the water on and off. In electricity, we would call that a switch. Okay? And notice the switch actually disconnects from the circuit here. Okay? And you can have some line here. Maybe it's crooked, right? And the water has a tough time going through that. Okay? That actually stops the water or keeps the water from going whipping around really, really fast. In a circuit, we have this thing called resistance, okay, which actually is what keeps the, in some sense, it slows the flow. It actually makes it so that the circuit runs properly. If we were to have, say, a light bulb, the resistance would be the light bulb. The light bulb would be providing that resistance, okay? And by the way, one of the reasons you don't want to actually just connect a wire straight from one side to the other of a battery is because there's very little resistance in a wire, okay? And so much charge will flow through there that it heats up a lot. Heats the wire up, heats the battery up, and not so good for it, okay? All right. Now, here's what I want you to do. I have 1, 2, 3, 4, 5, 6. Here, I'll give you the D battery. Wait, are there 6 D batteries? It might be easier. Yeah, it's actually going to be easier with the D batteries. OK, as I said, I think I told some of you guys, they only gave us 6 light bulbs. So take 1, 2, 4, 6, 8, 10, 12. OK, take 1 light bulb per 2 of you. OK, so you get a light bulb, and then you guys have to share a light bulb. And then keep passing this around. Please don't drop them, because I've only got 6 and they break. OK, so take 1 per 2. And then same thing, you can grab a battery. In fact, everybody can grab a battery. I do have some AA's if you want. Battery, battery, battery. There's, what, 8 of them in here, I guess? OK, take a battery. OK, and then you could combine them, but don't do that with the light bulbs, because and then here's some more batteries. Okay, if you guys want to use a D battery, you can. But here, I tell you what, you take a AA and a D, and you'll see that you do this. And you get a AA, and then he's got the D, and you can swap. And then, OK, you have a battery, 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 and then one for you, and then you guys will have a battery like that. Oops, you guys have those ones. And then who was it? Was it James that did all the stripping of the wires? OK, James is going to pass around 6 wires to everybody. Here's what I want you to do with these wires. I want you to, one of you guys, to take the light bulb and just make it light up. OK, with 1 wire and a battery. And I want to see if you guys can do this.
1 wire?
1 wire, the battery, and the light bulb. And you can make it light up. OK. And by the way, so what Nicholas is doing right now was, oh, there, he actually had it. Don't. Oh, there we go. 1 per 1 group did it. You guys both know how to do it now? Okay. OK, some people, nope, not quite. Now you're touching one end of the battery to the other. And remember how that'll warm the battery up? And that's probably not so good. So you don't want to do that. So it's got to be something else than touching the battery, the wire from one side. 1.5 is pretty constant in there. Oh, yeah. Oh, nice.
Just as right.
Got it, sir.
Did you get it? All right, good. All right. This is harder. For some people, this is harder than you'd think, just lighting a light. Did you get it? Let's see. Let's see. I don't see any light.
Just a second there. We had it. This filament blew. We had it.
You say so. Did you guys get it yet? Nope. See, now you're touching both ends of the wire to the battery, which doesn't work. There we go. All right. You guys got it. You guys almost got it. Did you guys get it? Andy, you guys got it? Bobby, did you guys get it? OK. Notice something about this. There's a metal part there and a metal part around the side. That on there. Touch one side to the bottom of the battery. Touch one side of the bottom of the battery. I'll hold this up here. You touch the other side to the side of the battery, the other side of the wire to the side of the battery. See if that works. There you go. See, it's the side of the battery? All right. That's good. Did you guys get it? Okay, good. OK, tell you what. Eric, you want to go around and just collect 6 of those and put them back in the baggie? Where's the baggie? The light bulb baggie?
Yeah, right here.
Okay, so I tell you what, just pass the light bulb sideways.
Put it back in.
Yeah, for now you can put it back in. Okay, so some of you guys had a little bit of difficulty with that, but that's okay. Let me show you how I would describe this one here. Okay, here's the battery. Okay, and it's got the little positive side on it. Well, not even that. It's just a little nod there for the positive side. This is the positive side. This is the negative side. Okay, you've got your wire here. Okay, a circuit has to be what we call complete, and there has to be a path that can go from the one side of the battery through whatever you're doing, in this case a light bulb, to the other side of the battery. Okay, so most of you guys finally figured this out, that if you stick the bottom of the light bulb right here, which has a little metal piece on it right there, okay, and then there's, let's see, where'd the light bulbs go? Okay, then there's a little black section in here that's an insulator, by the way, like that, okay, and then there's the rest of the light bulb, which is kind of like that, right, and then the bulb itself, okay. What you have to do is you have to make sure that the bottom piece there connects to the battery, and the wire actually connects to the side of the battery there, because the side of the side of the light bulb, the side of that light bulb is metal too, and that's part of the connector. And by the way, in here you have your little filament in there like that. But let me draw it like this. Let me draw it nice and big. Okay, here's the light bulb, like this. Okay, and down here is the bottom part here, and then there's some insulation in here like this. Put the insulation like this, like that, so that that's actually not touching the red part there. Okay, here's what it looks like inside the light bulb. You've got a wire coming up from here, going to your little filament in there, and then going to the side of the bulb, like there and there. And those two pieces of metal are not touching each other directly. Now when we connect the battery to the battery, looks like this. And then the battery goes like this. Do you see how we have one complete path for the electricity to go? It starts like, let's say it starts here, and it goes this way, and then here, and then through the filament, and then back down, and then here, and then ends up back at the battery.
Complete.
And you got to make a complete circuit. Yeah, question, Tyler.
Yeah, so the current is actually going from the negative side around and into the positive because the electrons are what's moving?
Yes, we actually, let's see. We say that the flow of charge, the electrons are doing the flowing. Okay, so they actually are going from, well, let's see. They actually are going from the positive side, getting kind of expelled off the positive side, through to the negative side. That's the way does that make sense? I'm pretty sure that's the way the current, we say current is. Benjamin Franklin's actually the one who described current for the first time, and he's the one who made up which direction it flows. I think he actually got it backwards from the way the electrons actually flow, as it turns out. Okay, and here's a question. I'm not sure. That's on the next page. Oh, not up here. There we go. And let me erase. OK. So chemical battery, by the way, chemical batteries, there's chemical disintegration of this zinc or lead or whatever. I think these ones might be, like, I don't know what these are made of, actually.
All made of zinc, sir.
These ones are made of zinc? Yeah, I think they do have zinc in it. But this is alkaline, so I don't know what that means exactly. It doesn't say what's made in. I don't know. I'm not sure. The energy stored in the chemical bonds in the chemicals itself is what gives you the electric potential energy, or the potential. OK, we now know how to light a light, but it's much easier when you see it this way, and this guy actually works for you, right? OK, we already talked about what makes a D cell different than an AA. Electric current, which we all just produced because of the light bulb there, it's the flow of charge. Okay, it's when charges actually flow. Now, as it turns out, the charges themselves, the electrons, are not like flying through the circuit. It's kind of like one electron goes a little bit, bumps into another electron, which goes a little bit, bumps into another electron. That's really what's going on. Okay? In metal, you do have conduction electrons. Okay? The electrons are actually conducting, but it's really that kind of bounce, 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 bounce thing. In fluids, you can get electric current because of the ions themselves are actually doing the same sort of thing. The ions break up into individual charges, and they flow. We measure current in this thing called amperes, or you might have heard it as amps before. Okay? By the way, they say it's the amps that kill you versus the voltage. So if you get like electrocuted when you stick your fingers in the socket, right? Bad idea. Okay? What's happening is there's a lot of charge flowing through your body. That's what messes your heart up. Okay? It's not the fact that it's many, many volts. We already talked about 5,000 volts in this thing. It didn't kill any of us, right? So it's really the amount of energy in it through the fact that we're getting it through the current. 1 ampere, 1 coulomb of charge per second, or 6.25 billion electrons in 1 second. That's a lot, okay, for 1 amp. Now, by the way, the little, like your iPod, generally charges with about 1 amp. Okay, that's about the max charging that it's going to get. And you notice that it gets pretty hot when you charge your phone up. It's because all this energy is going into your phone, and there's some losses, and it gets comes out as heat. However, the actual speed of the electrons, okay, is very slow. What that means is, okay, like I was saying, the electrons are bouncing off each other. The individual electron will kind of slowly make its way down through the wire and then back around, okay, to the other side of the battery. But it's actually a pretty slow process. It's really what we call the electric signal, or the electric field itself, which goes near the speed of light, actually. So when you turn the light switch on, bing, the electric field is created through the entire circuit almost instantly. But each individual electron kind of slowly makes its way down thing. In lights, it doesn't at all, because it's alternating current, which we'll get to in a little bit. But in a regular, like DC direct current system, like the battery, it's kind of slow. You know how long? So in your car, you turn on the car, right? And there's lots of circuits in your car, but let's say there's one circuit that goes from one side of the battery through, let's say, the headlights, and then back over to the other side of the battery. You know how long it takes an electron to get from one terminal of the battery all the way to the other? It's not a split second. It's actually like, I don't know, a few hours. Because one electron's bouncing against the next one. And then it gets bounced by another one, so it moves a little bit more. And then it bounces against another one, so it doesn't move. So over time, it tends to drift in one direction. But it takes a long time for that one electron to go all the way through the circuit. Does it really make a difference? Depends how you think about it.
So if the circuit is always closed, how do batteries lose their charge?
If the circuit's always closed, once the chemical energy has been used up, just because the electrons get back to the other side doesn't mean that it goes back into the system. It's actually losing energy as it goes along. So it's how can I describe it? When you've got all this chemical energy built up. Okay, things go through the circuit, do some work on the circuit, whatever, come back. They just don't end up like going back into the system where it's causing more energy again. I don't really know how else to describe it than that. Yeah, we kind of explained it a little bit.
One is positive, one is negative.
Well, this isn't really polarization in that case. It's not quite the same as that, because these are like this. That's more just static electricity. This is called like a battery is much different. But just for what it's worth, it doesn't. Just because it's connected, that actually is making it lose energy versus making it like gain it back just because it's a complete circuit. I'll have to look that up and get a little better. Let's look at this though. Which of these statements is true? Electric current is the flow of electric charge. Electric current is stored in batteries. Both are true or neither are true?
Both are true.
Both? What did we say current is? The flow of charge, right? Do we actually store current? No. It's kind of like saying you're storing the flow of water. It's not. You're not storing. You're storing water. You're not storing the flow of water, right? You're storing energy in a battery. You're not storing the current. The current happens when you connect a circuit, right? So it's not. You're actually storing energy. Okay? The voltage produces the current. Okay? And the battery moves the electrons already in the wire, not necessarily those in the battery. You know, we already talked about where the electrons themselves come from. The point is, you're not storing current. You're storing energy, which turns into a current when you do an experiment. OK. Aha. Electric current. The electric current that we have in the battery, okay, is what we call DC, or direct current. In other words, it goes in a path in one direction, and that's the direction the actual current flows. Okay? Alternating current is very interesting. It actually goes back and forth, back and forth, back and forth. So instead of having a current that's exactly the same, you actually get a current that is positive, then negative, then positive, then negative, then positive, then negative, then positive, then negative. That's what's coming out of your wall. Okay? And that's and the reason it's well, it's different, and the reason we have electric or AC current in our houses, there's a couple different ones. We'll get to one right at the end of the class where we talk about how it's easier to convert voltages up and down with AC current than DC current. And that's actually one of the main reasons we do that. But just keep in mind that DC current, nice straight line path. AC current, it's like on, off, on, off, on, off. Yeah?
Just a random question. Can you technically have a negative current ever?
Sure. You can have a current going one way in a wire, and then it goes the other way in a wire. And these lights are fluorescent lights. The power source is alternating current. What it's doing is, see how it goes up and down and up and down? Whenever this line crosses the little axis here, that means there's no current. Well, it means there's no current at all. Okay? First the current goes positive, then it goes negative, then it goes positive. In the middle there's no current, which means it's off. So it's all the way on, all the way off, all the way on in the other direction, all the way off, all the way on in the first direction, etc. These lights actually flicker on and off 50 times per second, because the number of times this goes, like the amount of time from here to here is 1/50th of a second. In the US, it's 1/60th of a second, by the way. It's 1/50th of a second from here to here. Here, you can't notice it. Although some people say that fluorescent lights give them a little bit of a headache. It might be because they notice their brain somehow notices it. They've made lights a little bit better that actually stay on between this cycle. And that's one of the nice things about like incandescent lights, like regular old light bulbs. They actually, by the time it switches, the light hasn't dimmed at all. It just hasn't had time to dim. Okay? These lights, they can go on and off 50 times a second. Yeah, Tom.
So that's with the 60 times a second.
Mm-hmm.
That's why when you have an American alarm clock that plugs into the wall,
yep,
you plug into a transformer over here,
yep,
so then it'll work. You don't fry it.
Yeah.
That's why the time gets jacked up.
It gets jacked up by how much? Instead of 50 hertz, so in the US we've got 60 hertz. In Djibouti we have 50 hertz.
So it's 1/6
Mm-hmm.
a second.
1/6 a second. Okay, how about this? In 1 hour, which is 60 minutes,
Okay.
your clock actually thinks it's only been 50 minutes.
Yeah.
Yeah, that happened to me when I moved to Australia. I didn't even know. I didn't think about it until I did that. Your clock, for some reason, a lot of alarm clocks actually are based on the frequency of the electricity, right? And what's interesting about that is actually that it's based on the frequency, and so therefore the power companies know this. And when you're generating electricity, it's tough to make this exact at 50 or 60 times a second. It's just difficult to do that. At the end of the day, they've been counting how many have gone by. They have a way to like speed it up or slow it down a little bit so that it gets to exactly the right number at the end at midnight. So throughout your day, your alarm clock might be a second or two off. Then by the end of the day, it catches back up because they've adjusted it so it's going to hit it right at the thing. I don't know if they do that anymore, but they used to do that anyway because most things like alarm clocks needed to know were based on this. I'm not sure why they still do it. They've got quartz crystals which will do it perfectly good without using that. So probably cheaper. It's probably why they do it.
My alarm clock was 7 hours behind.
7 hours behind because you forgot to change it? Yeah, exactly.
So if your fluorescent light bulbs are flickering, is that because the gas inside has actually like, kind of settled and electrons and protons have come together and makes
Yes, when you When it flickers, yeah, exactly. When your light flickers because the gases inside have stopped fluorescing. Yeah, exactly.
Okay.
Exactly, they've stopped
What's
charging.
the issue with fluorescent lights when you have the switch off, but it's still flickering?
Ah, that's a good question. I wonder that too. I'm not exactly sure. To tell you the truth, why when you turn the lights off, sometimes it keeps flickering. It's either because, well, I don't think it's because it's a bad circuit. I think what's going on is, the actual, well, something with the way they store a little bit of charge in there, so that you don't. It's the way the light's built. So it only does that for like a couple hours, right? Tops.
The one in my rack does all night.
All night?
So I just twist it off.
Maybe it is a bad circuit. I don't know. Maybe something's wrong with the circuit. But I find it hard to believe it would do it all night. But I'm not sure why. Not sure why. So what's interesting about, we use alternating current from the wall, right? Most of the stuff that you have, like your computer or your television or your Xbox or whatever, all run on DC current, right? So it's interesting these days. So most of our stuff runs on DC current. The things that don't are things like a vacuum cleaner that has a motor in it. Anything with a motor in it does that. And by the way, do you ever notice when you turn on like the vacuum cleaner, sometimes the lights dim a little in your house, right? That's because the motor itself is actually creating kind of a what's called is it a back current? I forget exactly what it's called, but it actually messes with the current in the rest of the house because it's the motor that's doing that. No, it's not a backfire, but it's I forget exactly what it's called. But anyway, that's what happens with a motor. But most of the stuff in your house is not based on AC. It's based on DC. So interestingly, DC current is what we create in solar panels. So you'd think that maybe someday, if we all had solar panels, we'd just not worry about this whole AC current. We just go to DC. But we'll see if that happens. Do you have a question?
Do you know how solar panels store energy? Like
Solar panels themselves don't store energy. What they generally do with solar panels is either they put it into some sort of batteries, which is not really normally what they do, but they actually convert it to alternating current and then feed it into the power grid. So the power grid just kind of takes it up. Now, here's another thing about power that we'll get to. When the power company creates power, it's not storing any of that power. You're using it. Somebody is using it somewhere. So every time somebody flicks on a light, some power station has to work a little bit harder, right? Because there's no storage in the system. It's just they just regulate how fast things need to turn to get the exact right amount of power. And it's a little tricky to do sometimes. And actually, it's very tricky to do from what I hear. But they need to do that. So the power on base here actually comes from the generators, correct? Pretty sure that's where most of the power comes from on base here. Why they made it 220 volts, I don't know, or 240 volts, I don't know. Because we're all Americans here and we all have American stuff. I'm not sure why they didn't just make it 120, but who knows. But anyway, they generate it here. So same thing here. If in the middle of the hot day, or right when everybody gets home from work and they all turn the air conditioners on, the power generators here have to work harder. Why? Because there's no storage in the system. They just have to work harder to deliver power to everybody. And they've got it down pretty well at this point. Okay. All right. Okay, we mentioned this earlier, electrical resistance. This describes how well a circuit resists the passage of electric current. Okay? Some things have a very high resistance, some things have a very low resistance. If you have something with a very low resistance, it may do something like generate light. So your light bulbs have a pretty low resistance. They generate light. A toaster is just a wire, basically, that goes through the system, or that the current goes through. And it's a very low resistance because you want lots of current and generates heat. So you get your toast, right? Resistance is it's the ratio of voltage to the current, okay? And we actually measure this in this thing called an ohm. Or I won't use green. Measure it in a thing called an ohm, okay? And here's the formula. Do I have the formula on the next page? I do not. Yeah, what is it? I think it's voltage equals IR, okay? Or, well, if we talk about the resistance, right? The resistance is the ratio. Resistance equals V divided by I. Right? V equals IR.
Correct. Current is the I,
Right.
voltage resistance.
Yeah.
Voltage divided by resistance.
Right. That's what it says in the book, right?
The current is the voltage
Voltage equals
divided by resistance.
the current.
The
What? Go ahead.
What are you writing? The voltage would be current times.
Current times resistance.
Yes, sir.
Okay. So then if we do it, we could also say I equals V over R, right? Or we could say V equals, R equals V divided by I. All right? Resistance V over I. Voltage equals IR. In other words, and by the way, I is current. Okay, we've got voltage equals the current. Why do we call I current? I'm not sure. We always did. Okay, the current times resistance. Make sense now? All different ways we do this. Okay, we measure this resistance in ohms. Okay, an ohm is a Greek letter omega. Looks like this. Like that. You've seen that most before?
Yeah.
If we say something is 7 ohms, that's the resistance of whatever we're talking about. Okay. See all these resistors here? Most of these, this one's tough, but most of these you can tell what the resistance is by knowing the code that the colors give you. I forget what it is. I never memorized them, but I think red and, let's see. I forget exactly what it is. Yeah, orange is like,
Yeah, there's a certain combination.
there are. I always forget what it is. I guess I'm a bad electrical engineer if I don't know that, but you can look it up. I always look it up. There's an iPhone app that tells you.
I'm sure there is.
Of course there is. Okay. All right. Here's what affects how much resistance a wire has, for instance. A thin wire, it's harder to get electrons through it, so it's got a bigger resistance. A nice thick wire, okay, it's easy to get electrons through it, so it has a very low resistance. Okay. If you look at the wires coming out of like the generators over there, they're really thick because you don't want your wires to have much resistance. Okay, you don't want that to do it. The type of wire. Some metals, like copper, has a very low electrical resistance, so it makes up some connecting wires. Rubber has a pretty big resistance, so it's used as an insulator. Now, we already talked about it. It's not used on the high voltage wires. Temperature also changes the resistance. Things that are higher temperature have a greater resistance. Things that are lower temperature, things can flow, electricity can actually flow easier in it. Surprise, surprise. Question, Andy?
Even the shape of the wires, for example, if you take a copper wire,
Mm-hmm.
you coil it.
If you coil it, we're going to get into coiling in a little bit later, what happens with coiling. But yeah, the shape doesn't really affect it. It's more the thickness of the actual wire, the cross section, which is what you talked about before, of the wire itself. Okay. All right. We've also got two other kinds of interesting conductors here. We've got semiconductors, which is why we have all the computers in the world, right? Because computer chips are made out of semiconductors, namely silicon. Okay. And nice thing about semiconductors, you can vary how much they insulate or conduct. It's pretty cool. Okay, you put a little charge on there and do it. It got some people the Nobel Prize in physics because they figured that out. You've also got superconductors, which means that at a low enough temperature in most cases, you have zero resistance in that wire. It's hard to believe, but you can actually have a wire that's zero resistance. Okay, superconductors. Pretty cool. Pretty cool stuff. Okay. All right, here we go. We have Ohm's law, which is the relationship between current, voltage, and resistance. Current, I equals V over R, V equals IR. This is the big one. We already mentioned it, but this is the big formula. It means in a wire at one point, if you know the resistance and you know the voltage, you can figure out how much current is flowing. If you know any two, you can get the third. Okay, just like that. All right.
So resistance doesn't matter in the length of the wire?
Resistance does matter for the length. A longer wire is going to have, what do you think, more or less? More resistance, right? Yeah, which is, by the way, that's one of the reasons that if you have a really long extension cord, you want it to be a little thicker. Because the more resistance your extension cord has, the lower the voltage is, number one. And number two, the more potential for it is to heat up, which you don't want to do on your extension cord. Do that. OK, All right, so this formula is a pretty simple one here. I equals V over R, or V equals IR. It's an inverse relationship between resistance and current, direct relationship between resistance and voltage. So let's look at our check question. When you double the voltage, what happens to the current?
It doubles.
Doubles. Easy, easy, easy. Okay?
So
Yep.
if we stack two batteries on top of each other, it's going to be 3 volts.
Two batteries on top of each other is 3 volts. And you don't want to plug those into the light bulbs because they'll blow up. Well, they'll burn out. Yep. Yep. Two voltages, yeah. 2 batteries like this is 3. Whoops. Like this is 3 volts. Like the positive to the negative and the positive on this side. That's 3 volts. Don't do it the other way. That's 0, right? Yeah. So you can get to that. OK. There you go. OK. Aha! I promised you the other day we'd talk about this. OK. Ohm's law and electric shock. If you get, like we talked about earlier, if you have current passing through your body, you can get a shock. Fair enough. The electric potential difference between one part of your body and the other part of the body depends on condition and resistance. Your resistance sometimes can be as low as 100 ohms, which is not much at all, and all the way up to 500,000 ohms. Sorry, yeah, 500,000 ohms. OK? If you, I wish I had an ohm meter here to show your resistance, but I don't have one. I normally carry one, but I don't have one, like on base here. And I left them at home because why would I need one here, right? Not like I'm going to teach physics or anything while I'm here. If you lick your fingers, you can actually make your own resistance go down between your fingers, right? You can do that. And you can, if you're dipping in salt water or something like that, you can do the same thing. But here's the big question. Why isn't this bird sitting on an open, unshielded wire, why isn't that bird dead?
The wire neutral?
Nope, wire's live.
The bird's a good insulator.
Nope, bird's not a good insulator. His feet are pretty good. Can't figure this out?
It's not touching anything else.
Well,
Nothing's grounded.
OK, we talked about this the other day. Nothing's grounding it. That is true. If the bird had a little wire which went all the way and got stuck in the ground, he'd be dead. That's because the ground and the bird and the wire create a complete circuit. And by the way, it actually is the ground. As it turns out, we make instead of having like a negative side and a positive side for the power company, they make it really easy. They say that the ground, the literal ground, Earth, is actually their negative. And they say that the wire is the positive. And when you plug your plug into the wall, one of those wires, just do the two, forget about the ground one for a while because that's a little misleading. When the two plugs in, one plug goes to the wire. The other plug goes to a wire that's in a pipe into your ground outside your house. Believe it or not. Right into the wire. And then that is what we call the ground. And it's literally the ground in that case. OK. So in this case, the circuit happens. And what it is the power station is over here. So here's the power station generating all the power. Let's see. Looks like this, right? And he's got the wires here. Power station takes one of its wires and plugs it into the ground. And the other one, it sends the power to you, or the electricity to you. You put one of your wires into the ground, and then the other wire connects to connects to your stuff, and then connects to the wire that the power company gives you. What happens is because these are both at the same potential, that's where you get this complete circuit. It's not really like electrons are flowing back to the power company through the ground, but it seems like that. So it's kind of odd. But anyway, so part of it is that the bird is not grounded, right? But let me draw a stick figure bird on here. OK? Let's see. Let me do it this way. Here's the bird, whoop, right? And the bird's body like that. And then one leg here and one leg there. Wouldn't you think that electricity would go whoop through the bird's heart and the bird would die? Whoops. No? You would think that, wouldn't you? Well, as it turns out, the bird's perfect. There you go. The bird has like lots and lots of resistance. The wire has almost zero resistance. So there's no reason for the electricity to go through the bird when it can more easily go through the wire. See how that works? So that bird's perfectly fine because Urites not grounded to the ground, and any electricity that might go up one leg into his body and down the other leg isn't going to bother because it can go right through the wire itself much easier. Okay? So that's the reason the bird is perfectly fine.
But if like a squirrel touched a bare wire, it would break.
Nope, it's fine. Squirrel can hang out on there, right? There's squirrel, 4 legs hanging out right there, right?
On a bare wire?
On a bare wire, sure, same thing. Squirrel has lots more resistance than the wire.
So we can't.
Now, if the bird was like somehow opened its wings up and it was a really crazy bird and had big long wingspan and went boop between those 2 wires, and they happen to be at a different voltage, then he'd be fried. And sometimes you see squirrels that like jump between wires, and they don't, and their tail is like still touching one wire when their feet touch the other wire. Zzz, they're dead.
That means they died.
Yeah. Yeah. What's that?
Then it falls.
Yeah. Then it's dead. Yeah. So, okay, that's the bird. Okay. Now we're going to get into electric currents or circuits. Okay. We already talked about it. We already built some electric circuits with the light bulbs. Okay. Any circuit that's a closed path where electrons can flow is called a circuit. Okay. The circuit has to be able to provide continuous flow, no gaps. And we already did this. We already made a light bulb light with a battery and a single wire. Okay, I already did that. Okay, now here's the interesting one that we're going to spend a little bit of time on this. I could spend days teaching you guys about this. There's 2 ways to hook up, say, light bulbs to a battery. Okay, and I'm going to show you a little video, a Hewitt video, that talks about this. But take a look at this way. Here's the battery, one side of the battery. This is a lantern battery. Okay, I've actually got one. Let's see. Hang on. I better use it. Christian, like, especially came in and said, "I've got the battery. I'll give it to her." Okay. So this is just a regular lantern battery, right? And it's got 2 sides here. One side says negative, one side says positive, and this happens to be a 6-volt battery. Okay? 6-volt battery. All right. We can hook up lights like this. We have the battery. It goes through a little switch, and then it goes up to one light bulb, which connects directly to another light bulb, which connects directly to another light bulb, and then back to the battery. Okay? We call that in series. And the reason it's in series is because it's one after another after another. Makes sense that it's in series, one after another after another? Mm-hmm. Okay? What's the voltage from this side of the battery to this side of the battery? What did we say? 6 volts. Which means what's the voltage from this side of all 3 lights to this side of all 3 lights? 6 volts. What's the voltage across each one? 2 volts. Okay? So as it turns out, if these were 2-volt bulbs, let's say they're 6-volt bulbs. Like they work best with 6 volts. If I've connected one bulb to here, it would be perfectly bright. Well, now if it's in series, what happens? There is more resistance, and they're dim because only 2 volts goes across each one. Okay, 6 total, 2 across each one. That's in series. Ever see light bulbs that are in series like this? Where? Christmas lights. I think they might have gone to a different method now. But they used to be that you take one of the lights out, the whole string goes dead. Because wouldn't it be true if I took one of those out, there'd be a gap between those 2? It'd be dead. Okay? It's like a switch. Okay? They used to do Christmas lights that way. Some of them might still be that way, but that's the way it goes. But they've figured out the voltage for the whole line and then made the light bulb perfect so when all the light bulbs are there, they're perfectly lit. Okay? This one wouldn't be that way because it's going to be more dim, like Eric was saying. There's another way to connect these. This is a little tricky to see, but here's what's going on. Each side of one bulb is connected to the one of the terminals. The other side of all the bulbs is connected to the other terminal. So can you kind of see? Well, you can't really see here. It's tough to see here, but what it means is I would have one bulb like this, and then another bulb also like that, and a third bulb also like that. What's the difference between each bulb now, or the voltage on each bulb?
I mean, they put 3 switches there.
They did put 3 switches there, actually. So let's take one bulb at a time. What's the voltage when the switch is closed? What's the voltage across one bulb if it's connected here to here? 6. I put another one on in the same form. What's the voltage across that one? No, also 6, because it's from here to here. And we know there's 6 from here to here. If I put a third one on, like the same thing, what's the voltage from there to there? 6, right? Well, that's kind of cool, because now if each bulb wants 6 volts and gets 6 volts, they all end up perfectly lit. Here's the interesting part, though. In this case, okay, we have all 6 bulbs, or all 3 bulbs, on the same line here. It is a bigger resistance, and what it's doing is it's actually they're kind of dim, and there's not much current flowing. Each bulb here is perfectly lit. So is there less current or more current?
Less resistance.
Less resistance, more current. Even though you put more bulbs in there, it's less resistance because they're what we call in parallel. And you can kind of see they're in parallel to each other, parallel to each other. Okay? Let me do this. Let me show you the Hewitt video that describes this as well, because I think he does a pretty good job with talking about why this is the case.
Do you know what's in there?
Do I know what's in the battery? This actually may have other smaller batteries, believe it or not.
Yep.
That's what I've heard.
Yeah, the 6-volt ones I think have.
Some of them do. Some of them definitely
yeah,
do.
some of them have, they're filled with AA batteries.
They're filled with AA batteries?
Yeah.
Oh wow. Okay.
I can't remember how many, but.
See if I think this is the one.
That liquid that's in like a car battery.
What's in a car? That's like sulfuric acid or something like that. Yeah. Here it is. Okay. Okay. Tell you what, Eric, you hit the lights. I want to make sure you guys see this one well. Okay. So what he's got is he's got a car battery. Oops. He has a car battery. Oops. That you can kind of see there, and he's got 2 posts that go up. And what it is 12 volts from one post to the other. 'Cause it's a car battery, 12 volts. One post to the other is 12 volts, and he's going to do a little some demos on this with light bulbs. Pay attention to how he does it. If we need to, we'll go over it again so you can see it twice.
I'm going to hook this up like that, and lo and behold, it lights. What's the voltage across the lamp, gang? 12. What's the voltage across the lamp now? 12. What's the voltage across the lamp now? 12. In fact, you know what I could do? I could keep this battery in this room, and I could take these 2 leads, and I could bring them to the other side of campus. And over on the other side of campus, I could go like this, and I'd say, what's the voltage across the leads, gang? And what would you guys say? 12. And it would light up over there. In fact, what do you think a wire is? A wire is just 2 leads that come from some power source somewhere else. But you got one of these things cut off. You hit a switch, boom, you connect it, and you're on. See, it's like this. Turn the switch off, boom. Turn the switch on, boom. There's little clever ways to do that. But I've got 12 volts across that lamp no matter where I put it. Okay? Let's suppose I go like this, gang. Let's suppose I put another lamp in here. I'll put another lamp in series. Series, I'm using your word, gang, series. Huh? There's one right after the other. I should have asked you before I did it, will a lamp glow brighter or less bright? And you guys would have said anyway, less bright. And I said, what's the voltage across the 2 lamps? And you guys would have said, what's the voltage across 1 lamp? And you guys would say, 6. Yay, feels good, feels good. 6. 6 and 6 is what? 12, that's right too. If you take the 6 volts across this 1 ohm, what's the current in there? Oh, we got to go through that again. If I get 6 volts across there, and the resistance of 1 ohm, 6 amps. 6 amps here. How many amperes over here? 6. In fact, in this series circuit, how many amps right through this little point right here? How many amperes through a point right here? 6. And how many amperes flew through the battery? 6. 6. 6. 6. 6. 6. All the way along. How many amperes up here? None. This is not part of the circuit. My circuit's right through there. See what I'm saying? The current flowing through the circuit. And the circuit now has twice as much resistance as before. If it quite got twice as much resistance, what's the current? Half as much. Do you see? Ohm's law kind of says it all. Ain't that neat? All right, now here's what I'm going to do, and everyone's going to get this right. I'm going to hook another lamp in series, and I'm going to connect it up, and you're going to tell me brighter or dimmer. Dimmer. Is there anyone says brighter? No, nobody say brighter. And what do we got? It sure is dimmer. Let me ask you guys a question. What's the voltage across the whole system? 12. Okay? How much resistance we get now compared to before? 3. 3 times the resistance. How much is the current now compared to with a 1? 1/3. Ain't that neat? So now you got 1/3 of an amp. Huh? What's the voltage across one of these things? 1/3 of 12. 4. Okay? 4. 1 ohm. 4. All right. Do I have it right? Did I make a mistake? Did I make a mistake, gang? I never make mistakes. But we have 4 volts across here. Okay? 1 ohm, so we have 4 amps. What's going through here? 4. 4. Before it was 6, and first of all it was 12. So the current's getting less and less because the resistance getting more and more. This is a series circuit. I'm going to make a little change, gang. Look how come it's bright. How about I take a lamp now and I put it not in series but in parallel, like the rungs of a ladder, parallel, parallel. I'm going to hook this. What's going to happen to the brightness of that lamp when I connect this? How many say nothing?
What's going to happen to the brightness of this one when he connects that one in parallel?
Nothing.
Nothing.
My people, that's right. Because let me ask you a question. What's the voltage across this lamp?
12.
What's the voltage across this lamp?
12.
What's the resistance of this?
1.
So what's the current through this?
12.
12. 12.
It gets a little interesting on here.
What's the voltage across this lamp? 12. What's the current through there? 12. 12 divided by 1, get it? 12. 12 amps, 12 amps, 12 amps. So if you know amps, volts, I get mixed up again. The voltage is the pressure supplied by the battery, 12. There's 12 right through across these, from these 2 prongs, yeah? And I pick up the 12, 12, 12. The battery going to wear down fast now, gang, because I got a lot of amps flowing. If there's 12 amps flowing through here, how many are flowing right through here?
12.
12. It's like automobiles driving from a garage down here. And some of those automobiles go through here and come back. Some go through here and back. Some go through here and back. If 12 go through there and you put a little checkpoint right here, how many are going through here? 12. Okay? How many through here? 12. How many through here?
12.
How many through here?
24.
Ah!
Did you guys
What
get
is it?
that one?
Yeah.
12 cars go up this way. There's 12 going down here, down here, down here. At the little junction here, how many go down this way? 24, because 12 came up here and 12 came down, so it adds together to 24. Down here's going to be
36.
Yeah.
Right, there's 24. Guess you get the 12 from here, and you get the 12 coming down this street. Ah. How many through here? 24. How many through here?
12.
You guys are on. 12. How many through here?
36.
36. How many through the battery?
36.
Who's getting tired? The battery. The battery. More energy going out, no, more power going out. You get it? Okay? Think about these ideas.
Okay, so did that make a little more sense now? Okay, I wish I had a check question. I should have put this in. Check question. I'll ask you right now. How is our house for the clue done? Are our circuits here? Write this down. See if you guys get it right. Write this down. Just write down one, or put it in your brain. I don't really care if you write it down, but put it in your brain. Our houses, don't say it out loud. Are houses in parallel? Are the circuits in houses in parallel or series or some other configuration? Okay, parallel or series or some other configuration. Think about it before you answer. Okay, and if you need to, write it down. Okay, let's raise our hands. Who thinks the houses are in, what did I say first? Parallel. Raise your hand. 1, 2, 3, 4, 5, 6, 7, 8, 9. Who thinks it's in series? 1. Okay. 2? Think you said series?
I said both.
You said it's both.
Yes.
Well, all right. I mean, some circuits, I suppose. But as you plug into the wall, are you plugging something in parallel to the rest of the stuff in the house, or in series? That's really the question. What do you think? You think in series? Why?
In the wall?
I plug something into the wall. Okay. Does everything else in the house go dim?
No.
Or until I plug it in, is everything off? And then finally I plug my thing in and everything goes on? No, right? That would be series, because remember, series, it's one complete circuit. And if you take one out, everybody goes dim. So for those of you who said parallel, That's absolutely right. And you can see each one has its own switch. Remember, there's one switch for the whole house in series if you were in series. You are in parallel because every time you put something in there, it gets the full voltage from the house. Question?
So it's using more energy or more?
It does use more energy, sure. And every time, and your power, if you're your house and you keep your lights on all day, right? You get yelled at because you're using too much power because all the lights are on and all the lights are using more, too much power, right?
Then when would they use the series?
You only use series in certain circumstances for like light bulbs, like the Christmas lights, where they just happen to make everything correct, and they do it that way. Otherwise, you really don't see that. Now, you can make lots of different circuits that have series portions of them, just because that's the way you build the circuits. But in terms of plugging stuff in your house, everybody's in parallel. Tom, you had a question?
Now, are there some breakers that it'll control like all the outlets in a certain room?
Yes, sure. But what that's doing is that's saying, oops, go back here. That's saying for each room, you've got a circuit that has one big switch for each room, let's say. And then all those are still on the same one. How about your power strip and your clue?
Yeah.
Right? Is that in parallel or series, each one of those?
Series. Parallel. Because if you turn off the extension cord, you just...
Do they all go through the same? It's funny, the way they build it, it's just like the battery actually. Let me draw it like this. Your power strip looks like this, like that, right? And then it's got all the different like things here and here and here and here, like that. The wires going in there, there's actually two. You only see one, but there's two, right? One goes this way, the other goes this way. And notice that it's exactly like he did with the battery, except turned sideways, where here's one circuit, and here's another circuit, and here's another circuit, and here's another circuit, and you plug something in here, and the power goes through here, and you plug something in up here, and the power goes also through there. And see how there's two different circuits going there? There is an off and on switch like out here, which is for the whole switch. So that's what like your house. That one says nobody gets power, right? And so really, yeah, I mean, from outside, like from here to here, yeah, this looks like a series circuit if you didn't worry about everything in there, right? If you just said that's one thing. Sure, from outside it looks like a series circuit, but really each one of these is in parallel to each other. Make sense?
In the house of the circuit breaker, is that where the master power comes into and then it splits to its respective rooms there?
Yes, when your power comes in. But remember, the power company gives you 120 volts, right? Or here it's 240, right? And that goes in there. And then all it does is it says, OK, you're going to get one of those things, you're going to get the other, but it's all going to be on the same two lines. And that's why every time you turn something else on in your house, the little thing outside your house goes a little bit faster that measures how much energy you're using. OK? Good. All right, let's go through. We already kind of did these. Single pathway for series, parallels this branched pathway. Let's see. When you do things in parallel, we said that the actual current adds up together. Remember how we added like the cars? Okay, in a series it doesn't. It's all one thing of current. Single pathway for the current. Okay. All right. I tell you what we're going to do. I was going to do a little online or a little demo of this, but I think I'll wait to the lab where I want to do a lab. It's actually going to be an online one, I think, where you're going to be able to put lots of light bulbs in there and see the path, the electrons. It's pretty cool. It's a really fun lab. It's another one of those fat ones, but it's fun. Okay. All right. If we want to overload a circuit, well, if we happen to overload a circuit, add more, add more, add more. You put a little fuse down the bottom here. Okay, when you add too many things in here, the total ends up being more than the fuse, and then that's when it flips.
So what happens when the fuse sometimes is burned or cut off?
What happens? Everything goes off. Right?
What is the reason that the fuse went off?
Well, because the fuse is rated for so many amps. It says the maximum I can have is 10 amps. And then you put one here that's 5 amps. Well, actually, this is actually the maximum here we'll say is, let's see, there's 20. Let's say the maximum is 19. Okay, for some reason you got a fuse, it's 19 total. You put in this lamp, it's 2 amps. You're good, only 2 go through here. You put in 10 in this heater, now total of 12 go through here. Then you put in the toaster, and now you've got 20. 20 try to go through the fuse. The fuse says, I'm not having any of that, and either breaks or it's a circuit breaker that flips. And that saves your house from catching on fire. Because when wires have too much current in them, they tend to catch things on fire.
What is it?
Bad news.
What is it that's going to give if the amperage gets too high? Is it the wire is going to melt the insulator? And
Yes, the wire will generally melt the insulator or just heat up too much and do that. Or it'll melt the plastic around it or whatever. Yeah.
So when wires are rated, is it rated to the resistor, the resistant
Too many check questions.
casing, or to the wire itself?
When to the wire itself generally. Now your house, the certain width of the wires, skinnier wires have less ability to do current. And if you ever go into like doing electricity in your house, you'll have to know all the different currents and things and put the proper circuit breakers and so forth. Okay. All right. I'm seeing some. Let's take a break. So let's take a break right now. Come back in 10 minutes, and we'll keep going. We still have to do magnetism tonight, which is cool.
Staying late.
Good to go? All right. OK, so let's do 2 quick check questions and then talk briefly about power. And then we're going to move on to magnetism. So here's your 2 check questions. 2, identical lamps in a circuit are connected in parallel. Is the resistance less than the resistance of each lamp, the same as the resistance of each lamp, more than the resistance of each lamp, or some other value? Let's raise our hands for this. Who thinks the resistance is less when you connect 2 things in parallel? 1, 2, 3. OK, who thinks the resistance is more when you connect things in parallel? 1, 2. Who thinks it's none of the above?
I think it's the same.
Not answering.
Yeah, it's the same.
What's that?
You didn't say the same.
Oh, I didn't do the same. Who thinks it's the same? A bunch of you think it's the same. OK, let's go back and just look. In parallel. OK. Did we ask about total resistance? Is that what it was? The total resistance. OK. So the total current, remember Ohm's law. OK. The current equals the voltage divided by the total resistance, the voltage divided by the resistance. First of all, in parallel here, don't we have this 1 path plus 2 paths? It's the cars thing again, right? More cars are going, like some cars are going up this way, some cars are going this way, some cars are going this way. Like if 3 goes this way, 3 this way, 3 this way, how many go right here? 3. How many go here? 3. How many go here? 3. How many come back down here? 9. So there's much more current. So this is a big value, right? The voltage, did the voltage of the battery change at all? No, it's the same. So this value stays the same. What's the only way we can make the current go up as we add more stuff? The voltage has to go, or the resistance has to go down. OK, so in parallel, the total resistance is less. So you're absolutely right, Eric, and a couple other people who said, and Nicholas, I think, said it would go down. OK? Attention to detail, exactly. All right. OK, so the next check question, so it was less than the resistance of each lamp. OK? It says resistors in parallel are like extra lines at a checkout counter. More lines means less resistance, allowing for more flow. OK? Next question. Consider a lamp powered by a battery. Charge flows out of the battery and into the lamp from the negative terminal to the positive terminal with a slight time delay after closing the switch. Let's make that a big time delay after closing the switch. Or through both the battery and the lamp. Charge flows from the negative terminal to the positive terminal. Well, let's see. It is through the battery and lamp. OK, it's not out of the battery into the lamp, because the lamp's not somehow storing up current, right, or charge. The negative terminal to the positive, it's actually the other way around. I guess I should have said, generally goes from the positive terminal to the negative terminal. OK, so I guess we talked about that. Is there a delay? It is a very, very, very slight delay, but it's like the speed of light, basically, so it's really fast. Yeah?
Well, technically, it is going from the negative to the positive terminal through the battery.
Through the battery, it is. Yeah, good call. Good call. But it does go through the battery and through the lamp. OK. All right. Now, finally, electric power. Remember how power was energy per time? If you bicycled up a hill faster, you use more energy, or sorry, it feels more tiring, but you use the same amount of energy, right? Okay? It's all about how much time it takes. Power is the exact same thing. Turns out power is current times voltage. Don't worry about those details. Units, same as units power before, watts or horsepower. Okay? A 100-watt lamp draws 0.8 amps if you plug it into a 120-volt bulb. A 100-watt bulb draws how much amps in 240 volts? Yeah. It's actually, well, it's either 0.4 or 1.6.
120 volts?
A 100-watt bulb. Yeah, 100-watt bulb. Well, actually, I kind of lied. A 100-watt bulb in Djibouti,
220 then.
it's actually 100 watts, right? It's going to be the same current as it turns out. Okay? But the voltage is twice as much, so the resistance has to be half, actually. Okay? I think that's weird. Did I do that right? I never make mistakes. Like Hewitt, right? So yeah, if it's a 100-watt bulb and you've got more voltage, power equals voltage times current. If the power stays the same and the voltage goes up, the current has to go down. Right? Okay? So and if the voltage goes up and the current goes down, let's see. It would be, the current would be lower. Right? The current would be lower, which is fine. The resistance, on the other hand, let's see. If the current's lower, the voltage is higher. Resistance would be higher for the lower current. I'll have to think about that. Think about that.
So why don't they use the bulb and things like that over here if they're all about conserving energy and stuff like they seem to talk about constantly?
Well, we do here. These bulbs are like these bulbs. These ones are like these. These are fluorescent bulbs, so are these. So the ones in your clue are more or less these bulbs. They look like these ones, right? So I think they do. Most of them are. I haven't seen too many regular, like incandescent bulbs.
Well, I don't know. I have them in my house back home, but they all like start off really dim before
They do. They're getting better. They're getting better. If you buy new ones, they do get bright pretty quickly. But they do start out a little dim. It's just the way they're built. But eventually they're about the same, right? In the end?
Yeah.
Like after a while. Yeah. OK. All right. So that's electricity. That was like way too fast. Like 1.5 hours on electricity is just too much. Not enough time to cover all of electricity. But we gave you kind of the basics. Next, we're going to go into another fun topic called magnetism. And then finally, electromagnetic induction, which, as it turns out, is responsible for pretty much the reason like we're all able to live in a first world country. Okay, we'll get to that at the end. I think it's really cool, but it's a neat thing. All right, magnets. So here's a couple of magnets. Okay, magnets have two poles. What are the poles called? Positive and negative. East and west, north and south, or left and right? For magnets, well, which is it? North and south, right? Everybody says positive and negative because we've just been talking about positives and negatives for electricity, right? But it's not. You've all seen bar magnets before. One side of it says north. One side of it says south. And that's what the magnet is, OK? So it's north and south. Okay? This one happens to be a bent one. It's like if you took this one, bent it around, one side's north, one side's south. Okay? It's a horseshoe magnet. Yeah. You've got bar magnets. You've got horseshoe magnets. You've got ring magnets that look like this. You've got those tiny little magnets that are, what do they call them? Neodymium? They're like rare earth metals, really strong. Rare earth magnets, really, really strong. In fact, a hard drive in your computer has really strong magnets in it. If you've ever taken a hard drive apart, it's got really strong magnets. You actually crush your finger, well, maybe not crush, but clip your fingers and really, you can't hurt them. Yeah, by doing that. OK, norths and souths in magnets. OK. Turns out magnets do have a north and south, Okay? And you can't have a magnet without both a north and south pole to it. It's impossible, as it turns out. It's kind of like, they use this analogy in the book, it's kind of like a coin that has like either heads or tails and not both. And I don't mean like a fake coin that has like two sides that are heads. One is still the head and one's the tail, right? I mean, either way, it's got one side, it's got two sides to it. It's just like a magnet always has a north and a south. But what would happen if I took this magnet and I went and broke it in half? Would I have a north and then a south magnet?
No.
What would I have?
You have the same.
Both pieces
You gotta have north and south.
would have north and south. So look, if I broke it in half, this magnet would have north and south, and this would have north and south. Broken in half more, north, south, north, south. It's exactly the same all the way down. Keeps going like that. Now, eventually you'll get down to like the atomic size, but then it stops becoming a magnet. It stops being a magnet at that point. Okay? All right. So more regular magnets. Okay. So compasses are kind of cool. They're actually little magnets. Okay? And they're light enough and put in on a little pin and in some fluid or on a little bed of air or something, generally fluid. Okay? And they point towards the magnetic field of the Earth, which is interesting because the Earth has its own magnetic field. Kind of cool, okay? Used to be that before GPS came along, you'd have to know something about like compasses to be able to get around, right? You still learn how to use compasses in basic training, basically. Yeah, you still do it.
Man navigation.
Man navigation, exactly. So here's the question. In the diagram below, which one's the north pole of the magnet? Which one's the south pole of the compass needle? One says north. This one's the north pole of the needle?
North pole, so this is off though.
So what do we know about norths and souths? It's kind of like, what if I turn the south to south here, north here, and south here, what are these going to do to each other? They're going to attract each other. They're going to attract each other, right? Like that. Okay, north and south attract each other. If I try to do the south and the south, right, I can't even get them together because they're repelling each other, right? So if the north pole, north pole, whichever direction north is a north magnet, and the south pole is a south part of the magnet, of the magnetic field of the Earth, what is the point that in this little magnet, what's that one have to be?
South.
A south pole of the compass. So it's kind of reversed for here. That side points towards the north pole, which is a north. So if that's a north, then this is the south. It's kind of cool that way. All right. Would it surprise you if I said that magnetic fields also show an inverse squared relationship by now? No, they're the same.
Got a compass for you.
Oh, there's a compass in your phone. Yeah, your phone actually has a little real compass inside of it. I mean, it doesn't look like a compass, but yours says the other way. Yeah, the problem with compasses in general with the magnetic field of the Earth is when you have a building full of metal, like sometimes the magnetic fields get a little bit messed up, and when lights and currents and things in lights create magnetic fields of their own, so you might get a little bit messed up. Yeah, the battery doesn't have that, but you know what you could do? Here, try to turn your phone. This will not hurt your iPhone. If it does, I owe you an iPhone. Grab the magnet and put it near the compass and see what happens.
That's what I do.
There's no hard drive in there.
With the batteries, that would go whack.
No, well, battery's not a magnet. Did it do it? Maybe the battery is a little magnetic.
Too close?
No, it's
They're working or no? Oh, there you go. Did it go towards it?
This is odd.
Oh, yeah. Sometimes you gotta. It's probably because it's so messed up in here anyway. There you go. Okay, get it right nearby. No, go even closer. Right, close. Right next to it. Is it moving at all? No. Do it right on top of it. Right on top of it. Just put it right down on top of it. On top of the magnet. What did it say? It said, oh, you got to do it again, recalibrate it. Yeah, sometimes it does.
Why on the negative pole doesn't move the compass?
Mm-hmm.
I'm sorry, correction.
It's probably got a little bit of a magnet. It might have a little magnet inside of it. Might have a little magnet. It might be some kind of magnet in the battery. I'm not sure exactly. Okay. All right. Question for you. Check question. A weak magnet and a strong magnet repel each other. The greater repelling force is by which magnet? Stronger one, the weaker one, both the same? Or none of the above?
Equal. Stronger. Even Steven. No, we don't.
What'd you say, James?
I would say both.
Both the same. Why? This is actually a trick question. Not a trick question, but why? What do we know about forces? What about them? No, just regular forces. Any force comes in pairs. We had some dude had a law. Which law is the one that says that they're going to be the same size force? Yeah, which law was it? Remember? Third law. Thanks, Bobby. There you go. Okay. Yeah, they're both the same. This is Newton's third law. It's nothing to do with magnetism except the forces. Okay. So, plane. Okay. Now, magnetic fields. Okay. If you look at this picture, and I put the little magnet up there. Whoa, it actually stays. Haha. Those are what we call metal filings. Okay? And if you sprinkle those around, notice how you get this kind of cool pattern where the filings go in all different directions, right? Well, I set up something a little earlier here where I'll go around and I'll show you that I set up a little bar magnet and then a bunch of compasses around it. And as I go around and show you, notice which direction all the compasses are pointing. The little red arrows are pointing toward more or less towards the south. The silver ones are pointing more or less towards the north. And it goes around in this kind of circular thing. Can you see that there? Okay, kind of try to look at that. See how, if you look at the way the silver's all kind of pointing towards south, and it's kind of circular the way, if I had lots and lots of them, it would be kind of, they'd be going in a circle. Okay, kind of cool that way. You know? See how these are the reds pointing towards south, 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 and then this one's kind of going this way because this is the way the field lines are going this way, and it kind of goes in a circle.
So this is the magnet here, right?
That's the magnet right there. Yeah. Mike, I'm going to sneak past you here. Excuse me. Oh. Okay. All right. You guys take a look right here. See how the direction of all these little the compasses? That one's messed up. There we go. Ding. There you go. See it? Yeah. So you see how the red line goes that way, and then the red line goes that way, and then here it points up that way, and here it points down that way, and it's kind of circular in that sense. The same sort of thing. Can you kind of see it? Yeah. You guys see it here. Whoops. Okay. See how the red one there points towards south, points away from the red, points away from the north. And this south kind of points that way, red, kind of in a circle, like up on the board. Kind of the way it works, yeah. So it's all because the way the magnetic force lines are in a magnetic field. All right. So I think I can probably take that off. Turns out magnetism, and this wasn't known for a long time, but it turns out magnetism and electricity are really the same force. Well, not the same force, but come from the same ideas. Okay? For a long time, they thought magnetism and electricity were completely separate. Turns out they're actually much closer related, and magnetism is not a fundamental force like electricity is. Magnetic fields are actually produced by moving electric charges. Aha! So when we get moving electric charges, we get magnetic fields. Let's do a little foreshadowing here for a couple minutes from now. When we connect up the light bulb, are there moving electric charges in that wire?
Yeah.
Do you think that's going to create a magnetic field to some extent? It actually does, as it turns out. Now, it does. It creates a magnetic force, or a magnetic field, which you'll see. So actually, in some sense, it's called an electromagnet. We'll get to that. Okay? All right. When you look at a magnet, what's happening is there's little pockets of places around the metal, and it's only metals that really do this, okay, and only some metals. Like copper, not magnetic. Iron, very magnetic. Iron has these little pockets where all the little spinning electrons line up together, okay? And in this case, this is not this would not be a magnet. Because notice all the lines are going in different directions. They all kind of cancel each other out when it looks like that. Okay? If we magnetized this, all the lines would be going in the same direction. And in that point, it would be a north side and a south side. Okay? You can realign magnets. If I dropped this magnet a whole bunch of times, it would actually bang around the magnetic domains in here, and it would start to get less magnetic. So you don't want to do that to magnets if you can help. You don't want to bang them around, okay? Or heat them. The minute you heat a magnet, all the magnetic fields get all jumbled up, and you're done. Okay? The only way you can get it back is to take another magnet and like rub it against it, or let's see. There's one other way. The book says one other way. I forget what it is. You can either rub it against it, or have a really strong magnet, put the bar of metal in that strong magnetic field, leave it for a while, and it becomes magnetized.
Like degaussing on a ship.
Like degaussing on a ship. Yeah, degaussing on a ship. For those who don't know, when a ship, you have these big coils underwater sometimes, and the ships go over them to make them so they're not magnetic. Because when they are magnetic, things like magnetic mines and things tend to stick to them and blow up and stuff. So they try to do that. By the way, you can actually make. No, this is not going to work. It's going to work like this maybe. You can actually magnetize another piece of metal just by putting it in a magnetic field so that you can get another little magnet. This nail, once I take it off of the magnet, boop, right? Not magnetic anymore. But once it's in the magnetic field, you can actually magnetize that piece of metal by leaving it in the field.
Magnetize the nail by rubbing the magnet.
You could actually, yeah. Yeah, you could. Right. Okay. The first time I ever saw one of the, like a screwdriver that had the magnetic tip, I was flabbergasted. I was like, whoa, that's such a good idea.
Ingenious.
Yeah, it's pretty ingenious. OK. Why doesn't a magnet pick up a penny or a piece of wood?
Because a copper, well, where are the pennies?
Pennies made of copper and zinc.
Yeah.
Because it's not a good conductor.
Has nothing to do with conducting. They actually are very good conductors. But do they have those magnetic domains in them? No, only certain metals. Iron, for instance, steel has that kind of domain in there. Okay? And wood just doesn't have any magnetic domains either. Okay? How about a 1943 penny?
It's real copper.
Not copper. It's actually made of steel. For 1 year, they made a whole bunch of pennies out of steel because they were in the middle of a war and copper was very expensive. Yeah, you can actually, supposedly you can find some 1943 pennies. Like the first batch was copper, and the whole rest of them were that. So they're really worth a lot, like hundreds of thousands of dollars. Or a penny. Yeah, kind of cool. OK, so electric currents. We talked about this before. Electric currents and magnetic fields. Moving charges produce magnetic fields. Okay. A current, which we said contains the moving charges, because it's going from the one side of the battery to the other, will produce a magnetic field. So if I have a current flowing through like this, if I line up all the compasses around that wire, they all line up in a nice circle like that. Whenever I turn the power on. When I turn it off, those go back to pointing towards the North Pole. Turn it on, they all go around in a circle. That's kind of cool. Okay. When you reverse the current, they all go back the other way. I want to show you the video. It's Paul Hewitt doing some more stuff, but I'm going to wait on that right now. These are all currents going through wires. Okay, this one's that circular one. These are just the filings again. If you have a wire going in and out of the table, right, the filings kind of line up in circles around the wire itself, because it's always around the wire like that. If you have a whole bunch of wires in a coil almost, right, you get they kind of all follow this way. Well, they all follow this way. And notice what they're kind of adding together in the middle. Notice this. Doesn't that look like a bar magnet a little bit?
Isn't that the concept that they use on the trains?
This is the concept that you use for any electromagnet, right? This might be the North Pole, and this is the South Pole, and it's just an electromagnet. So if you do lots and lots of coils around, and especially around a metal piece of like ferromagnetic metal, you get a magnet. And that's how they make electromagnets. They just put currents through wires, wrap them in a circle around a bar of metal, and you've got your electromagnet. Pretty cool stuff. Okay? Pretty cool stuff. All right. Ha-ha. Now, this is a huge, huge discovery. I do want to show you that video, so hopefully we'll get to it. When you have current going through a wire, and it's in a magnetic field, while that current is changing, in other words, when it's starting up, you get a force on it, which is really cool, because if you can take a electric current and put it through a magnetic field and get a force, you can make cool things like a motor. This is what makes motors happen. You put electricity through a wire, you have it in the right configuration, and it provides a force on something else. And if you do it in a circle, you actually can make it so that it turns like a motor. So this is the basis for an electric motor. Very, 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 very important. Okay, it's like the reason the Industrial Revolution started was like because of this idea. Okay. And we'll get to the motors in a little bit. Magnetic forces in space. The magnetic field of the Earth is a very good thing for your health. Here's why. As particles, in other words, charged particles, come flying towards the Earth, don't they get a force on them from the magnetic field of the Earth, just like we said in the previous slide? As it turns out, they come flying in. Instead of going down and hitting you and maybe causing cancer or something, the magnetic field of the Earth goes, I don't think so. Whoop! They go flying out the other direction. Right? They get a force on them that happens to be against the direction they're going, and that turns them, and they never end up hitting the Earth. Some do, of course. But most go coming in and actually get kind of diverted by the magnetic field of the Earth. Very good for your health. Okay? All right, back to moving forces or magnetic forces on moving charges. One of the most important discoveries in the history of the world. You didn't think you'd be getting to the more important discoveries in the history of the world in this class, did you? Moving charge in a magnetic field feels a force. Why? Because that's how a motor works. By the way, generators, very similar, but the exact opposite. Here's how a motor works. Okay? You can go online and see lots of demonstrations of this. You have a little current, and you hook it up to this wire, which is basically a piece of metal. We call it when it's a wire. Okay? Put it in a magnetic field. Okay? And if you build it right, which is a little bit of cool engineering design in here. If you build it right, that current makes the actual piece of the motor turn a little bit as it goes through it, because it's in a magnetic field. And it keeps turning, and then it switches the direction of the current, and then it keeps turning around in a circle. And it does that every time it turns around, and it goes, and now you've got a motor. Okay? That's actually a motor. The battery is providing electric current, which is making the motor go. And then you connect your car tires to this, and you've got an electric motor. Okay? Or you connect your vacuum cleaner, or you connect your electric toothbrush, or whatever else is a motor in it. Right? Whatever has an electric motor, which is like a zillion things, right? This is how it's done. Just involves a fancier wire and a magnet. Okay? So all motors have magnets in them. I don't know if you knew that or not, but they have big magnets in them. Okay? And the magnets are there so that this process works. Pretty cool stuff. Okay? And that's motors in a nutshell. We also have this idea of electromagnetic induction, which is kind of the opposite. If magnetic fields produce forces on moving charges, then when you move a magnet near a wire, or move the wire near the magnet, you can get an electric current, which is exactly the opposite. Instead of, I'll go back here for a second, instead of making the battery turn the thing, if you go and turn this on your own with a crank, you actually can charge up the battery because you can create an electric current in here. That is cool. And that's also how we get the electricity to put into the power grid. Did you have a question? Yeah. No, go ahead.
So you said that we actually do something to it to we can create.
Yeah.
So it'd be like the windmill and the water thing.
The windmill, the water thing, monkeys that you train to turn a crank, whatever you want, right? That's how you make electricity. Okay? Except for solar power and whatever.
The windmill.
Well, the windmill is connected to this thing. That's exactly what Louis is saying. He's saying, look, you connect the windmill to this thing and make this turn, the battery gets charged up. Pretty cool. Or you plug your light up to it and you get power. right? That's all these wind turbines or nuclear power or coal power or whatever you use to make your power. That's how it works. It's turning a wire inside a magnetic field. That's where you get all our electricity, except for solar. Question, James?
I was just saying, is that how they used to do the old cars when you had to go in front?
No, that's the old cars were still gasoline powered. They just had instead of having a nice switch where it has a motor that starts it,
They just had a little crank.
you're actually doing a motor to actually you're actually turning the motor of the car over yourself. Yeah, good idea though. Okay, so here we go. I should have gone forward one. There's your handle on the same exact thing. A generator is a motor, and a motor is a generator. It just depends on who's doing the work, the battery or you. Okay, and you turn it, you get a little current, you turn your light bulb on. All power outside of solar power happens this way. Pretty cool stuff. And it was a huge discovery because we wouldn't have motors if they didn't know how this worked. And it was a completely like nobody expected this either. I mean, it wasn't like people sat around, oh, you know what, if I do this, this will probably happen. It was like completely unexpected. There was the video that I'll show you talks about the guy. It was a high school physics teacher, basically, who was like teaching class. And he said, this isn't really doing anything. A student came up after class and said, what if you do this? And boom, all of a sudden you get this stuff. He figured it out. It was pretty cool. Yeah. OK, so I wish I didn't spend only 5 minutes on it. But motors and generators, huge, huge idea in science. All because of physics, all because somebody figured out that magnets and electricity have this cool relationship to each other.
Like you said, the Industrial Revolution never would have happened without it.
Industrial Revolution was pretty much because of that. Now, I wanted to put a couple slides in here about the transformer, because we all have transformers in here, because we live in Djibouti and we have 120 volt stuff, and we plug it into, well, we want to plug it into 120 volts, so we get the little transformers like this thing. And by the way, this is heavy, and this is heavy because that piece of metal is what's doing most of the work here. Okay, this is a transformer, and what it is you have a piece of metal somehow, or something, okay, and you take a bunch of wires and you coil them around, and then you take another wires also on the same piece of metal, coil it around fewer times. Notice how there's like 5 turns here and 4 turns here. What happens is you put current into this one. It creates this magnetic field, okay? And note magnetic fields create current, right? So that magnetic field will now make a current in this other piece over here at a different voltage, as it turns out, because the number of turns actually means it's a different amount of voltage. Aha! So you want to make a transformer. You get a piece of metal. You coil up one. Let's say you wanted to make it. Twice, like we do here, right? You take it. You go around the coil. You do the primary one like 100 turns, and the secondary one like 50 turns. The voltage here is 240. The voltage here is 120, and you don't blow up your stuff. Pretty cool, huh? It's pretty simple, actually. I mean, it's very subtle the way they make these things these days, but it's, that's basically how you do it.
So
Okay.
could you step it up with the primary being 120, wrap it twice, and then your secondary wrap it 4 times and bring it up to 240?
Sure. Yeah, you could do it exactly the opposite, and you do it by. Really, what you could do is just turn the little thing around, because it's exactly the same. You just put the plug on this side and the power on this side, and then you've got 120 to 240.
So if this one, the
Yep.
primary here was 100, then the secondary would be putting out 80? Is that right? It's 5 and then 4?
In this one, yeah, 5 to 4. 5 to 4 relationship in this case. Okay. This is also why the frequency doesn't change, because it doesn't know anything about frequency. It's still got to vibrate back and forth the same amount. Don't worry about those details. Okay. So that's how a transformer works. The larger number of coils has the higher voltage. Okay. But the power is the same. You're not getting anything for nothing here. Just because you raised the voltage or lowered the voltage, you don't get any benefits except the voltage difference. Okay. Turns out that it's so easy, and this only works, by the way, for alternating current. It has to do with the fact that direct current won't create the permanent magnetic fields like this. So easy for alternating current. That's probably the main reason we have alternating current into our homes. Because of the power station, you generate the current at like, I don't know, 5,000 volts. Then you bump it up to 120,000 volts. You send it across to your house where you bump it down to 120 volts. The reason you do that is because you get much less or much more efficient the higher the voltage is as you transfer the thing. So hard to do for DC, very easy to do for alternating current, which is what transformers are. Okay? All right. Electric grid.
So that's why solar energy goes from DC to AC to DC so that it can convert it to a useful voltage?
Well, not really. The reason it does that is because the whole grid is already AC. It doesn't, you need it to go feed into the grid is what it turns out. So that's why the solar panels do that. Electric grid, voltage generated at the power station stepped up before being transferred across the country. And then other transformers make it go down to your house. And the only reason they do that is because it's more efficient to do it at a very, very high voltage. You don't lose as much energy trying to transfer that such a long distance. Okay? All right, and then finally, I think this might be, there's one more after this, how televisions and radios work. And the fact that I'm spending 1 minute on this at the end of the day is terrible. One of the most striking discoveries in all of 19th century physics, besides the magnet and electric induction for motors and generators, turns out that electromagnetic waves, in other words, a magnetic field creates an electric field, which creates a magnetic field, which creates an electric field, which creates a magnetic field. And when this happens, you get things like, oh, I don't know, light, radio waves, television waves, whatever, let's see, X-rays, right? All that sort of stuff you get from the fact that a magnetic field creates an electric field, creates a magnetic field, creates an electric field, creates a magnetic field, creates an electric field, or whatever, like this. Okay, it's pretty advanced stuff, but I just wanted to let you know the reason we know about radio waves is because of this electromagnetism sort of stuff. Okay, it's cool, cool stuff. Okay. All right. Oh, I actually skipped it. This should have been the previous slide. Transformers everywhere. These little guys are actually transformers. They transform 120 volts out of the wall down to like 6 or 9 volts. Then they convert it to DC so that you're plugging into your computer and it's DC. Ever seen those little cans on the wall on the thing? Those are transformers. Ever seen them blow out? They make a lot of noise. Yeah, big boom. Okay. Yeah. What's that? They have oil in them? Oh, okay. Probably cools them is what it does. Yeah. Cool. All right. So a lot of stuff tonight. Holy smokes. That was probably the most we've done in one day. Good job. And I'll see you guys, what? Saturday. At this point, yeah, no homework right now. I guess you're lucky. Just read the 2 chapters. All right. I'll give you the first project on, maybe I'll email it to you. You can start working on it if you want. It's going to be basically on the physics of something. You get to pick the something and talk about the physics of it. Okay? All right. See you guys later.